Photoneo is leading provider of industrial 3D vision, AI-powered automation solution, and robotic intelligence software. Since the foundation in 2013, the company's mission was to give vision and intelligence to robots all over the world so they can see and understand with a clear goal to automate monotonous and risky tasks by employing vision-guided robotics. We have delivered over 3,000 solutions worldwide, and our technology was recognized by the highest honors, including the Vision Awards in 2018 and Platinum Innovators in 2019. We have headquarters in Central Europe, Slovakia, with branches in USA, Kentucky, and China, Shanghai. Globally, we employ more than 200 people, and we cooperate with more than 50 distributors, which can provide you with the sales and technical support. Photoneo is constantly developing hardware and software capabilities in order to bring robotic eyes and robotic brains to push the limits of flexible automation to a new level. Our research and development team is always looking for new approaches, how to improve already cutting-edge technology in order to offer our customers the best 3D vision and robotic intelligence. The definition of vision-guided robotics is pretty simple. A robot that should be equipped with a sensor or camera, and if you do so, your robot should be able, with the involvement of the certain vision algorithms, to move towards this target. The growing need for smart automation has caused that 3D vision as an integral part of vision-guided robotics has continuously been expanding into new markets. Gradually, the 3D vision has entered application areas such as robot guidance, BIM picking, advanced object handling, depalletization, path correction, assembly, quality control, inspection, or shape evaluation. Photoneo has the capability to solve this application with in-house developed hardware and software, offering customers the most complete solution for the most advanced tasks requiring 3D vision. The entry-level product of Photoneo is a Foxy 3D scanner. Foxy 3D scanner is your go-to scanner when you are looking for high resolution and high accuracy scanning of static scenes. Its structured light projection approach provides output in the form of precise point clouds for fast localization of any desired part. The robustness of the scanner ensures superior quality of scans, which makes it best scanner for even the harshest environments. Foxy 3D scanner was awarded by the Vision System Design Innovators Awards program for its unbeatable performance and best-in-class resolution to speed ratio. It is using method that also belongs to triangulation approach, eliminates the scan object with a so-called structured light. The triangle spans between the projector, the scan object, and a camera. Because this method enables capture of a scene without need of moving any part, the structured light technology provides a high level of performance and flexibility. Sophisticated projection techniques are used to create a coded structured pattern that encodes 3D information directly in the scene. This information is then analyzed by the camera and integral algorithms, providing a high level of accuracy and resolution. The scanning volume of the Foxy 3D scanner family range from 15 centimeters up to 4 meters, allowing you to scan large as well as very small objects. You can get 3 million 3D points in every scan and an accuracy of 25 to 500 micrometers across the different models. Our advanced methods for ambient light suppression provide a superior quality of scans even in demanding lighting conditions of up to 20,000 lux. Thanks to its low weight of less than 1.5 kilo, The Foxy 3D scanner can be mounted directly onto a robotic arm, a very handy option if you need to scan a big bin with a smaller scanner from variable viewpoints or to get a detailed look at the bin corners. You only need a single cable to get both electric power and data connection, so-called power over Ethernet. The flagship sensor product of Photoneo is called MotionCam 3D and is the whole world's highest resolution and highest accuracy area 3D camera for dynamic scenes. It's your go-to device for applications requiring fast and robust 3D acquisition. Reconstruct accurate point clouds of various objects in a high level of detail without compromises on quality caused by vibrations, ambient light, or motion blur. Motion cam is especially suitable for scanning dynamic scenes moving up to 144 kilometers per hour. This makes it your ideal 3D vision companion for handling objects in motion. With new Photoneo patented technology called parallel structured light, we bring the state-of-art quality and resolution of structured light scanning into the 3D reconstruction of highly dynamic scenes. This novel patented technology uses a clever sensor design which performs the acquisition in one snapshot as opposed to the sequential scanning of a standard image sensor. This means that the power structured light method practically freezes the 3D scene in time. The camera works perfectly well also for static scenes. It can be used as a scanner for the static scenes. We at Photoneo started to work firstly on a bin picking application as the first problem, and we found out it is a bin picking on Wikipedia, which was referring to bin picking as the holy grail, the core problem in the computer vision and robotics. In the Oxford Dictionary, you will find the definition of holy grail as something which is very difficult to get. So if you think of it, it was not so many years ago when the majority of the bin picking applications were actually built on greenfield. What you need to do as a company, you need to acquire certain skills in order to build a bin picking application. So you definitely need to have a person who understands mathematics, geometry, robot kinematics, the person who is able to work with technical drawings, a person who is capable to program a robot. You need an operating system for running your software, and you need to have a solid software engineers to implement vision algorithms. You need to have a 3D vision sensor, and you need to be able to create the localization algorithms. This is a very wide variety of advanced skills, and it is really difficult to find a person which master all of these skills. And even if you find somebody, it would be a very expensive thing. If you want to build a team where each member master one of these skills, it's not going to be cheaper either. So in Photoneo, we were thinking if there's something we can do about it, and we found out there's actually just two skills which are available in the area of our customers, and it is a technical drawing and robot programming. So we created a tool which is designed for robotic integrators, and it's called Bin Picking Studio. In the bin picking studio, Photoneo is offering multiple localization approaches for different industrial areas, such as general industry, machine tending, plastic industry, foundry, logistic industry, and parcel handling or the apparel industry. In Photoneo, we believe that the best outcome coming from the 3D vision guided robotics application lies in the close cooperation with robotic integrators and customers. Therefore, we always want to express the possibilities, but as well limitations when it comes to the customer requirements on the bin picking application. After attending this bin picking studio training, you will have a unique opportunity to get the bin picking studio demo package for a special price. This will unlock you affordable access to experience Photoneo hardware and software for bin picking. Demo can be used for your testing and feasibility purposes. We can unlock this demo system whenever you decide to upgrade it to a full version of BIM Picking Studio. Again, welcome to BIM Picking Studio training, and I'm passing the word to my colleague, Patrick Bakita. Enjoy the event.
Thank you, František, for the introduction. Okay, I'm going to share my screen now. Okay, once again, thank you, František, for the introduction. My name is Patrick Bakita. I am BIM Picking Studio product engineer, and I'm going to be leading this workshop, this training, Master of BIM Picking. I would like to kindly ask you once again to ask the questions in the Q&A section, not in the chat. I will be monitoring the Q&A section, and once in a while, I will answer all the asked questions. Okay, let's start with the presentation. This is our approximate program. So we already had the sales introduction of the company and the products. We will be actually jumping between the presentation and the actual BIM Picking Studio, as we are going to be preparing a new BIM Picking project. You can see that behind me, there is a robot, there is a scanner on a construction. There is also a scanner on the robot itself. So we are actually going to be using two vision systems. So we are going to be using also scanner mounted above the bin and a scanner mounted on the robot. We will configure the BIM Picking solution. We will have a lunch break, and after the lunch, we will finish the configuration and run deployment. Okay, so let's talk about the BIM Picking Studio. What we are aiming today to do is to get to this page. This is the deployment page. So when you finish configuration of your BIM Picking project, you deploy the project onto the Vision controller. So the industrial PC that is running the BIM Picking Studio, and the application is then running, and you can monitor its current state. You can see the console where are the log messages. You can see the cycle time. You can see the visualizer, which shows you the real-time motions of the robot and the parts that are being localized. BIM Picking Studio is a web-based application. What it means is that it is running actually in a web browser, which has a lot of advantages. Most importantly is the remote access, because you can access the BIM Picking Studio from another device that is connected to the same local network. Our motivation. We have a lot of experience with deploying our own projects, our own integrations, and we also gather feedback from our customers to make the BIM Picking Studio as a product even better with each release. And we do that because we want to provide a reliable BIM Picking application for our customers. Some of the key benefits, as I was mentioning, the web interface of the BIM Picking Studio. BIM Picking Studio is very intuitive. It has visual representation of each step of the configuration. The initial setup can be done very fast, and it is very easy to use. BIM Picking Studio is built to not require any programming knowledge. Only the basic skills are required to be able to operate BIM Picking Studio. BIM Picking Studio also offers easy reusability of previous BIM Picking solutions. You can back up your existing applications, your BIM Picking solutions, and you can import them, export them, import them into another BIM Picking Studio. You can create the backups, and you can change what you need in a very short time. Beam Picking Studio offers a great deal of debugging tools for your to ease the manipulation of the Beam Picking Studio. It offers a wide portfolio of robotic brands. It has built-in calibration interface, and of course, it can use multiple scanners and multiple vision systems. We will get to that later. Here are some of the key benefits on the screen. So the success rate of the localization is very high. The Beam Picking Studio can be running basically all the time. We can achieve cycle times even down to 5 seconds, depending on the configuration of your beam picking application. And of course, we can do the oriented placing. Let's get to the description of the vision controller. So this on the picture is the vision controller. So the vision controller is an industrial grade PC. It's basically a classic PC. It has, this is the front side, what we are actually currently seeing. On the front side, the important parts are the Ethernet ports, which have dedicated functions, because through these Ethernet ports, the other hardware is connected to the vision controller. The other hardware is the robot itself and the scanner or the scanners. And also you can connect the vision controller to the local network. On the front side, there are also GPU ports on the motherboard. These are not used, just for the information. The ports that are used to connect your displays are on the back side. There are several configurations of the GPU ports, but every vision controller has a HDMI port and a display port. On the back side, there's also the power socket, and that's basically all the important stuff. Then there also are the USB ports for connection of the peripherals, so for your mouse, for your keyboard, and so on. Okay, so the basic beam picking application consists of the vision controller, which is the heart of the application, the brain behind it. The eyes is the Foxy 3D scanner, so the 3D sensor by Photoneo that is used to capture the scene to provide us with the point cloud. And also there is the robot. Beam Picking Studio supports several robotic brands. We will be working today with the latest version of Beam Picking Studio, which currently supports the robotic brands that you can see on the screen. So Yaskawa, ABB, KUKA, Fanuc, Kawasaki, and Universal Robots. Here you can see the exemplar hardware topology. So as I was already saying, vision controller at the center, then optionally a network switch if you are using multiple scanners, or you can connect the scanner directly to the vision controller. Then there is the connection between vision controller and the robot controller, and you can connect the vision controller to the internet or to your desktop PC, or you can use a network router to connect it to the local network. Beam Picking Studio configuration steps. Okay, when the vision controller boots up, it is running the Ubuntu 18 as an operating system, and all the Beam Picking Studio related stuff is located on the desktop. So I'm going to show you the desktop of the Beam Picking Studio. So this is it. There are several folders. There is a folder, example solutions, where there are backups, basically the beam picking solutions we provide on the vision controller. You can import them and you can check them out. You can use them for inspiration. as they contain some basic approaches in beam picking application configuration. Then there is folder File 3D Cameras. In this folder, there are 4 folders. Each folder is a fake scanner. So you can create a folder in here that will be the name of the scanner. And you can put saved scans from the real scanner in here. And when you disconnect the scanner, you can use these recorded scans as a fake scanner. So you can use a scanner even if it is disconnected to, for example, test localization or even the beam picking itself in a simulation mode. We'll be talking about it later on. Let's get back to the desktop. There is the scans folder. This is serving for saving of the scans. So currently there is 1 saved scan, and there are the shortcuts for launching, restarting, and stopping the beam picking studio, because as an application it is running all the time, but you can always stop it or restart it in case of a problem. Okay, let's get back to the presentation. The first login and the initial setup of the beam picking studio. When you first get your beam picking studio and boot it up, the beam picking studio will be launched automatically, and you will be greeted with a welcome page. The welcome page serves for the initial configuration of the beam picking studio. What that means is that you choose your installation time zone, which configures the time on the vision controller, the system time, and you also create beam picking studio accounts. What is mandatory is to create the customer's master account. The customer's master account has the highest privileges in the beam picking studio, aside from the Photoneo admin account. And you can also create other user accounts with different levels of privileges. These accounts can be also created later on. When you finish configuration in the welcome page, you can log in to the beam picking studio. As I was saying, the beam picking studio is a web-based application, so you can access it and it is running on the vision controller locally, so you can access it on the localhost web page, or you can use this URL address. And of course, you sign in with one of your created accounts. Okay, so let's log in to the beam picking studio. I'm already logged in, so I'm going to log out. This is my account. Moment, please. Okay, so we are logged into the beam picking studio. You can see that we are on the solutions page. This is actually the beam picking studio version 1.6.1. So the first patch release of the beam picking studio, we added Stäubli robots among the supported brands. So there's actually 7 supported robotic brands in the latest release. And there are already 4 beam picking solutions. We will get to them later. Okay, I will put the presentation in slideshow mode so we can see better. The beam picking studio navigation bar. So on the top side, on the top of the beam picking studio, there is the navigation bar. It has several pages, several buttons. The first is the solutions list, which you get to when you log into the BIM Picking Studio, and it contains the BIM Picking solutions. Then there is the deployment page. The deployment page is, as the name suggests, used when the actual solution is deployed, so where the BIM Picking application is running. There is the Foxy interface, which is an interface for Foxy Control, which is an application that is used to operate the scanner. And there is the network page that is used to configure your network interfaces for communication with the scanner and the robot, and also the other devices on the local network. So you can configure your network interface to be connected to the internet or to another device. And in the top navigation panel, you can always see what process is currently running. BIM Picking Studio recognizes several processes. So there is the deployment, where the application is currently running. There is the calibration process, when a vision system of a solution is being calibrated, and also localization process, when the localization is being configured. In the right corner, there is the menu button, and there are some more options. There is the user profile, there is the account management, where you can create and edit the profiles. And there is also a very important link to documentation. So anything if you have any problem with BIM Picking Studio, you need to find some information, please go to the documentation and try to find the answer to your problem. But if you are not able to find the solution, the answer to your question, you can always contact our support. We are here and we will kindly help you with anything you need. There are also two more shortcuts to download BIM Picking logs. The BIM Picking logs for support, and there are also BIM Picking console logs, so the logs on the deployment page, the messages that you can download for your use. Okay, let's go through the pages in the BIM Picking Studio. There are already two questions. The first one is, in other words, where is the BIM Picking Studio web-based app hosted? It is hosted on the Vision controller. So it is running locally. You don't need to be connected to the internet, nothing. It is running on the local host. But if configured properly, the BIM Picking Studio, and then then you configure the BIM Picking Studio to be on the same local network as, and you connect to this local network, and there are other devices on the local network, you can use the IP address of the network interface to access the BIM Picking Studio. So I will talk about this a little bit later. And is this the IPC UI that you are displaying? Yes, I am presenting actually from the Vision controller. So as it is a classic PC, I can use it for browsing the internet, whatever. I mean, the BIM Picking Studio cannot be installed any program, but the basic programs are here, and the web browser mostly. So you can use this as a regular PC. Okay, so let's get to the BIM Picking Studio and check these pages. So this is the solutions list. Here are some pictograms for the solutions, so you can recognize them more clearly. Each solution has an ID, unique ID. This ID is very important because through this ID, the robot identifies the solution and it can request the solution to start or to stop and so on. You can see what robot is selected to be used in each solution, who is the author of the solution, where was the last notification, several flags you can see that there is a ready flag. It is also a shortcut to launch the Beam Picking Studio application, the Beam Picking Studio solution, sorry. So any solution that has the ready flag can be deployed. A new solution doesn't have this flag, so it cannot be deployed. And there are some actions that can be done. You can delete your solution, you can export them. So create a backup, and you can duplicate them and modify so you can have multiple versions of the solution when you want to change something or test something. Two more buttons to create a new solution or to import a Beam Picking Studio solution from backup. Also, naturally, you can import older backups. So you can import Beam Picking Studio solutions from older releases of the Beam Picking Studio. They are all compatible. There is also the news page where we show the release notes of the latest release. Okay, the deployment page. There is a drop down, and I can select one of my configured Beam Picking Studio solutions to deploy it. Then there is the Foxy interface, and I should probably talk a little bit more about the Foxy control. So the Foxy control is the application that is used to operate the scanner. So you can see that there are a lot of scanners on the network because we are at our headquarters. At the bottom, there are the fake scanners. And our scanners that we will be using today are this one and this one. And there is a lot more. Okay, so you can connect to a scanner. I'm already connected. And I can trigger a scan. Here's the visualizer. You can see the point cloud. I'm going to add a little bit of brightness. So you can see that I have two beams prepared with two different parts that we will be working today with. Okay, we will get to the Foxy control a little bit later too. So let's go back to the Beam Picking Studio, and this is the interface for the Foxy control. So I can connect to the scanner also from the Beam Picking Studio. It gets connected in the Foxy control too. This interface in the Beam Picking Studio is a very simple one. It serves just for triggering scans and saving them. You can also save the scans from the Foxy control, but sometimes it is more suitable to download a scan from this interface. You can save the scan in 3 different formats. I would like to ask you, if you are sending a scan to our support, always use the PRAW option, because in this format, there are all the raw data that are often needed, so we can do all kinds of stuff with the scan and help you with your problem. Okay, so this is the interface. You can also play with some basic parameters, but when you are configuring the scanner for operation with Beam Picking Studio, you should always use the Foxy control, as there are all the settings that might be needed. Okay, let's go to the network page. And let's actually start the configuration. So here are 3 interfaces: the robot, the scanner, and the network. The robot interface is the IP address on the Vision controller. And here is the robot controller IP address. So this is the IP address that needs to be copied from the pendant, from the teach pendant of the robotic controller. So you configure the IP address on your robot, and you just write it down into this field. And you need to make sure that your robot interface, so the IP address of the Vision controller, or the interface for the robot on the Vision controller, is on the same subnet. You can see that the subnet mask is 24, so the first 3 numbers are the same, and the last number is different. you can optionally use different ports. Why? Well, there are two communication channels between the robot and the vision controller. Each channel, this is a TCP/IP communication, and on each side there is a server. So on the vision controller there is a server, and on the side of the robot there is a client that connects to this server. And this server, this is the beam picking server, is running on a default port. And also there is the other channel where the robot controller creates the server. This is actually called robot state server, and this server provides us with current state of the robot. So where is the robot, where is the position of its tool center point, and also what are the current values of rotation of individual joints. And we need this data for all kinds of stuff. So there are these two communication channels, and if this configuration is done properly, the robot should be available. So I'm clicking the test connection button, and I can see that my robot is running. The network is configured properly, and the robot is available. The scanner interface provides two options: DHCP server or static IP address. The Photoneo scanners come from production with a DHCP client option, which means when you connect them to a network where a DHCP server is running, they will be assigned an address from the range which the DHCP server is using. And I already had the DHCP server, so we can check it in the Foxy control. So for example, this scanner I am using, the UD059, you can see that it got IPv4 address, and it is always in this format. Only the last number is different, so it is running. This DHCP server is running on this subnet. But I can, and it is recommended, I should use a static IP, so the communication is more robust, because the DHCP server can change the IP address of the scanner, and that can cause some instabilities and so on. But nowadays the vision controller is configured, and also the Foxy 3D scanner, to be using the IP version 6 address actually. So this is the preferred option. So this is just a fallback. If something goes wrong with the IP version 6, then the IP version 4 is used. If you have the network configured properly, you will be seeing both these addresses. If you have incorrect setup, incorrect configuration of the scanner interface, this address won't be displayed. Your application, your scanner should still be working properly. The connection should be good, but it is recommended to also have proper configuration of the IP version 4. The address of the IP address of the Foxy 3D scanner is configured from the Foxy control. So I am going to just select my scanner, and I'm going to hit configure. And here you can select either the DHCP client option, which is the current option, or you can provide it, you can configure it to use a static IP and several levels. Once you fill this form and apply the settings, the scanner will reboot, and it will be accessible on that IP version 4 address. Okay, and then there is the network interface. there is, so on the scanner interface, there was the DHCP server option and the static IP. And on the network, there is DHCP client, because we are expecting that when you connect the vision controller to the local network, which is running a DHCP server, that the vision controller will be provided with an IP address from the DHCP server running on the local network. But you can also configure it to use a static IP address, and that is recommended and should be done in case you are using remote access. So when I want to access the vision controller, the BIM Picking Studio, from another device, for example, from another PC, I should configure the network interface to be using a static IP address. So I will type the IP address in here. I will also put my device on the same subnet. And when I configure the devices correctly, I can go to this IP address on my other device, on my other PC, and I can work with BIM Picking Studio from there. So that is very, very usable when you are not near the BIM Picking Studio and you need to check something, mostly for the monitoring. Okay, so this was the network page, and there are the other options. So the user profile, you can see that I am the customer admin. So this is the account with the most privileges, and in the account management, I can create another account, and there is the documentation option. There you can find a lot of stuff regarding configuration of the vision controller and the robot, and also the BIM Picking Studio solution itself. Okay, let's talk a little bit about the solutions page. So these are, we already did that basically. So I was mentioning the flags. So there are two more. When a solution is deployed, it has a flag deployed, and there is factory default flag. And this solution, which is marked as factory default, actually Photoneo support uses this flag, and this solution cannot be modified. So you can always duplicate it and modify it, but there will be also always this solution that cannot be modified, and you can come back to it in case you need to. The deployment, the network interface, I will add one more thing. As we were talking about the interfaces, there are other ways to access the BIM Picking Studio remotely, and not just through the web browser of your PC, but the vision controller is always during the whole runtime running a VNC server. So you can connect to the server with arbitrary VNC client. You just need to know the IP address of the vision controller, so of the network interface, and a password. And this password, we will provide you with this password on request. You just need to ask our support. BIM Picking Studio is also running TeamViewer, and this software is mostly used by our Photoneo support in case we need to connect to the vision controller to help you with something. Okay, so the configuration of the network, and let's get to the Foxy control once again. So the Foxy control, I'm going to go to this scanner that is mounted above the bin. The robot stands in the way a little bit, so I'm going to move it. Okay. Okay, so I'm going to trigger a new scan. Oh. Okay, so there are three visualizers. There is the 3D viewer, where you see the actual point cloud. There is the depth map, so you can use the mouse to go over the picture, and in the right on the right side you can see the distance from the scanner, current pixel value. So I can see that, for example, this part is 1.3 meters from the scanner, and there is the texture. So this is how it looks. This is the black and white texture image. Okay, let's back to the 3D viewer, and let's talk about the main options. So the scanner is running, it is not paused. I can log out from it. There is the options to trigger a scan. So I just did another scan. The free run is just basically continuous scanning. There is the option to save the scan, and the scan will be saved into the folder I was talking about earlier. So in the scans folder on the desktop, configuration of the saving options. So you can the record button. I skip the record button, so you can record scans, every scan that is being taken. Carefully with this option, because you can fill up the vision controller and the memory of the vision controller, which you certainly do not want to do. So you should always just manually save some scans that you need, and monitor the memory usage of on the vision controller. The saving options, so you can configure the format and the compression level of for the scans, some diagnostic options, tools, and so on. The important stuff is on the settings pane on the left side. So beam picking, the Foxy 3D scanners come with several profiles. What is a profile? A scanning profile is a set of parameters on the scanner. And these factory profiles, there is the default one. So this is the profile that is most suitable for wide variety of applications. And the other profiles that are configured for some use case. For example, there is the profile that for strong ambient light suppression. There is a profile for filtering of noise on shiny materials. So you can check these profiles, or when you are not able to configure the scanning parameters yourself, again, you can ask our support, and we will be happy to help. Regarding the settings, there are basic and advanced capturing settings. Let's start with the resolution. Currently, this is the half resolution. You should probably always, well, not probably, but always when you can, use the lower resolution if it is enough for the localization to have a good performance, because the less points, the faster computation times and the faster cycle time. So if possible, you should use the half resolution scans, but you can always go to the full resolution if needed. And let's check the difference. So you can see that there is a lot more points. The point cloud is much better. That basically depends on your application, on the material of your parts, on the model of the scanners, because there are several variants, several sizes of the scanner. It depends on the distance. A lot of stuff comes into play. There are other options, the shutter multiplier, which basically multiplies the patterns that are being projected, the scan multiplier, which does average of the scans, of multiple scans, and you can use that to get rid of some of the noise from the scene. Always monitor the scanning time on the right bottom, in the right bottom corner, because the scan take a lot of time if you put high values in these fields, and you need to do the scan in most cases you need to do the scan in each cycle. So in each cycle you are losing time if you configure the scanner improperly. So try to keep the acquisition and computation times as low as possible. The transfer time should be pretty low, depends on the size of the point cloud, of course, but I will just mention that you need to use category 5 or 6 cables. You need to have gigabit Ethernet switch if you are using a switch to connect multiple scanners, because the point clouds consist of a lot of data. It's basically several dozens of megabytes, and you need this data to be transferred to the vision controller instantly, as fast as possible. Some advanced options for filtering of the point cloud for the exposure time. So if you are scanning some dark materials, you definitely need to increase the exposure of the laser, because you need more light to be projected onto the dark material to get some reflection out of it. You can turn on the ambient light suppression, the coding quality. So mostly I would suggest using high, which is optimal. It means there will be 8 patterns projected. And then some other options which can be used. I will mention the region of interest. So you can search down here. It is under processing settings in data cutting. So if you are scanning a large scene, and for example, you need to have the scanner mounted as it is, and it is scanning the robot also, you don't want to do that because the point cloud is actually a collision object in the beam picking studio. So anything scanned, the robot won't collide with it. And if the scanner takes a scan of the robot, then there is naturally collision between the point cloud and the robot. So you can use this region of interest if you are not able to mount the scanner in a way that it will not be scanning the robot. You can use the region of interest to actually crop the point cloud. And this way also you will be cutting down from the scanning time. Okay, I am going to be using this default profile of today, so I'm not going to configure the scanner right now. Maybe later if I see that something could be better. And now about the supported mount options. There are some questions regarding the robot. We will be talking a lot more about the robot in a minute, so I'm going to answer them in a while. So the mount options for the scanner. I already mentioned this. There are as you can see in the presentation, on the right side, there is a video. There is a scanner mounted on the robot itself. So this is the hand-eye approach. And today we also have, so we have this option, and we also have a scanner mounted above the bin. So we will be using both scanners today to show you both supported options. Each of these configurations has some disadvantages and mainly some advantages. When you have the scanner above the bin, the robot is not so limited in its movement. That is one big advantage. Also, you don't need to stop when you are taking a scan. So in a basic bin picking application, you do a scan, you pick the part when the trajectory is calculated, and right after you leave the bin, after the robot leaves the bin, so it is not moving in the area between the scanner and the bin, you can and you should trigger a new scan as soon as possible. So in time, meanwhile the robot is doing the placing procedure, the bin picking studio can calculate the new scan, the localization, and do the path planning for the new objects. But when you are using the hand-eye approach, you need to stop with the robot because the scanner needs to be static during the scan acquisition. So basically, you are adding to the cycle time the amount of time that is necessary to do the scan, and that depends on the configuration of your scanner. So I would say the hand-eye approach is not ideal for the time critical applications. On the other hand, the hand-eye approach is very good when it comes to scanning small parts in big bins, because with big bins you need big scanners, but with big scanners you don't get so many details that you might need for localization of those small parts. But what you can do is that you can mount a smaller scanner on the robot, and you can get closer to the bin, to the parts. You can also take scans from multiple viewpoints, and that way it is much more likely you will be able to localize all the parts and empty the bin. Okay, and now finally, after the general configuration of the bin picking studio, we can start creating our new bin picking studio solution, which will be deployed at the end of this training. So bin picking studio solution consists of several steps. You can see them on the screen in the presentation. So there is the solution detail page. There is the robot, so where you select the robot which will be used. Then you need to define the gripper. You need to define the objects, the parts that you want to pick. You need to define gripping points. So where on the part the gripper will be activated. So where will be the gripping point, the contact point between the gripper and the part. And then the grasping method, which is a strategy for picking. So how the robot will move during the trajectory, during the bin picking trajectory that is being calculated. Then the vision system. That's a whole another chapter. We will be talking thoroughly later. Then the calibration of the vision system, because the localized parts are in coordinate system of the scanner, but the robot needs them in its own coordinate system. So we need to calculate the transformation metrics, or in other words, calibration metrics for each vision system. So we can report the position and orientation of each part in the space, in the coordinate space of the robot. Then there is the environment page. So here we can define our virtual environment and also some settings on the settings page. And the deployment is just another shortcut to easy deploy the solution from any configuration page of the solution. Okay, solution detail. In the solution detail, there are 3 tabs. There is the actual detail page where you provide the name of the solution, you provide the unique ID. As I mentioned earlier, this ID is very important because when you want to deploy a solution, the robot will call a request. It will send a request over the TCP/IP, and it will provide a parameter, which is the ID of the solution, and the vision controller will recognize that the solution should be deployed. Then there is option to add some attachments, small attachments to the solution. For example, you can put your robotic program here. And so when you do a backup of the solution, you will also have the backup of the robotic program. And you can track the activity in your solution in the activity log. So let's create a new Beam Picking Studio solution. Create new. Okay, my solution will be called BPS training. The solution unique ID was generated automatically. So 1 it is. I can provide also some description for my solution, and I can save it. And that's all. This is basically all on the solution detail page. On each page, you will be notified about the missing parameters for deployment. So right now, there is a lot of stuff that is still missing. But in time, we will have everything done. Let's get back to the presentation. The configuration of the robot. We need to select the exact robot model from the database of the robotic models, the exact model that will be used in our beam picking application, because this model, it describes the whole kinematics of the robot that is needed not only for the proper visualization, but mostly for the calculation of trajectories and most importantly, the collision checking. Here is the basic overview of the communication with the robot. So there were those 2 questions in the Q&A. So does there have to be custom software installed on the robot? Yes. On the vision controller, there is a interface for each supported robotic brand. And on the robot itself, there needs to be installed what we call a robot module. So the robot module is unique for each robotic brand. It's brand specific because each robotic brand uses different programming language. And this robotic module is just a set of functions. So several files, depending on the robotic brand, a set of functions that extend the library, the API of the robot, and then these functions can be used to communicate with the vision controller. So in your standard robotic program, after you install the robot module provided by Photoneo, you can, for example, call a new function that will connect the robot controller to the vision controller. After you are connected, you can call another function that will initialize the vision system, because each vision system needs to be initialized, and then you can call another function. Basically, I'm describing the standard beam picking application. So you connect, you initialize, and then you just go scan request. You request a scan to be taken by the vision controller or by the scanner. And after the scan is done, you just request the last thing in a basic application, and that is the trajectory. So the scan and trajectory after the vision system has been initialized, it's just the scan and trajectory requests that are repeated in each cycle. And after the trajectory is requested each time, of course, there is a function that will execute the beam picking trajectory, the received beam picking trajectory. Another question was, which communication protocol interface should have a KUKA robot controller to communicate with vision controller? KUKA, in the documentation, there is an integration guide for each robotic brand, each supported robotic brand. And at the beginning, there is prerequisites section. So you can see what needs to be installed on a robotic controller board. Options, if they are non-standard, needs to be installed on the robotic controller for the communication to be working properly. So for the KUKA, in the latest version, there is also the EVA supported, and that is a little bit different. So KRC we want now. So for KUKA, you can see that you need to have system of version 8.3 or higher, and you need Ethernet KRL. KRL interface of version at least 2.2.8 or higher for communication with the communication with the vision controller. So some requirements for the system version and this Ethernet interface. Okay, since we are already here, the integration guide. So the prerequisites section where you check what you need to do beforehand. Then the robot module can be obtained, each robotic brand, from our support. So you just write an email and we will provide you with correct module for your version of Beam Picking Studio. There is configuration of the robotic controller. So basically just the network configuration and installation of the module. And there is the description of the API. This is brand specific, so this is more technical. The description of the individual functions I was mentioning is in the requests in the Photoneo Robotic API section, and these are all the supported requests. So the functions that can be called from the robot to command the vision controller to do some stuff. We will be talking about this during the deployment, so we will get back to it. Then there's also a description of the example programs, because not only we provide the required library of the functions to communicate with the vision controller, we also provide several example programs for basic beam picking applications. There is also the how-to tutorial, how to run the example program, and there is the section migration guide, which will let you know what needs to be done when you upgrade your Beam Picking Studio, whether you need to also upgrade the robotic module, and what changes were done in the robotic module, and whether you need to do some steps yourself aside from the uploading of the new module. Okay, so let's go to the robot page and select our robot. I can choose the manufacturer. I'm going to be using a Kawasaki robot. I can also directly search if I know the model name. This is RS007L long version. each robot has a status. This status says that the green one means that the robot has been tested in production, and the orange or yellow one means that the robot has been validated in a simulator. So the robot model was not tested in production. It should be still working properly. In case, in rare occasions, you find that something is not behaving correctly, just let us know and we will check the robot model. Okay, so let's select the robot model. And I have already installed the robotic module using the integration guide. So the robot is ready to go. So this is all that needs to be done. The gripper. You can see that on this vision controller, there is a lot of grippers already defined. You can, when you define a new gripper in Beam Picking Studio, it can be chosen in another solution. So this is a shared database on the vision controller. I'm going to be adding this magnetic gripper, but from scratch. So add a gripper, I need to give it a name. So let's call it gripper for training. I need to provide a CAD file in STL format. So browse, and this is my gripper. I'm going to save it. So now, right now, the model is being uploaded, and it takes a while because a volumetric model is being generated automatically. What it means is that a volumetric representation of this gripper is generated because we need it for collision checking of the gripper with point cloud, because sometimes, or better to say mostly, in most cases, you need to allow some amount of collision of the gripper with the point cloud, because there is some noise, a little bit of noise. The gripper needs to touch the part, or maybe touch a little bit the other parts. No collision, no major collision happening. Just there needs to be slight contact between the gripper and the point cloud. And that means that we cannot reject all collisions, but we use this volumetric model, and we can then set up a threshold that will say how much of the volume of the gripper can be in collision. This is in most cases just a small number, just to account for the noise and for the light touches of the gripper and the stuff around it in the grasp, in the moment of the grasping of the part. Okay, the model is correct. I need to have the Z, so the blue arrow pointing upwards. So you can see that the coordinate system is in the origin. The origin needs to be where the robotic flange is, because the gripper will be automatically attached to the robotic flange, so to the model of the robot. And I need to define my 2 points. So Beam Picking Studio is not working with the 2 point that you have configured on the robotic controller. We need our own definition of the tool center point. The best option, though, is to calibrate your tool point on the robotic controller, because the real gripper does not need to be, in most cases, it is not perfect, and this model tends to be perfect, or you need to have the exact model of your gripper. So when you calibrate your gripper, I'm just using the arrows to get to the approximate position. So this is basically, this is where the tool point is. So it is in the center of the magnet. But after I calibrate the gripper on the robotic controller, I know the exact values. So I know that this should be 91. No offset in the x-axis, and this is 157, I think. Okay, so this is my 2-point, and let's save. But this gripper and most grippers have a property, and it is that this 2-point is symmetrical. The gripper itself, it is not. You can see that it is crooked. This shape of the gripper allows us to go near the walls of the bin, because under the gripper, from this point of view, there will be the robot, and the links of the robot might be robust and big. So if the gripper would just be it would not be offsetted to the left side or to side in general, we would have difficulties going near the walls. There would be collision with the wall. We could not pick the objects that would be very near the walls of the bin. But this shape allows us to get pretty close to the walls of the bin, and the 2-point is symmetrical. So it is not important. It does not matter how the gripper is rotated around the z-axis, so around the blue arrow, when we are picking, because the magnet is still the same. It's still the same area that will be attached to the part. So we will enable rotation invariance. And you can see that the default parameters are basically correct, because the axis of symmetry is by default the z-axis, and I have 8 steps of the symmetry. So right now, my gripper can rotate into this another 7 positions. So from 0 to 7, there are 8 invariances. And that basically means that I have 8 options now, 8 configurations how to pick a part when I come to it with the gripper. I can increase the number. This can be done. It is in many cases necessary, but you need to keep in mind that with increasing configurations, with the increasing number of configurations how to pick a part, the number of computations that needs to be done increases, and the path planning can be slowed down. So this needs to be kept at a rational on a good number. So 8 or 12, I will keep 8. 8 seems like a good default value. Okay, save, and I got a little bit carried away, and I skipped the presentation part, but I think I covered everything. So here we have the robot model database. You can see that there is a lot of robots, and we can add another robot on request. So you just write us on the support again that you need another robotic model added to the BIM Picking Studio, and it can be done in a few days. And as I was saying regarding the robot module, that needs to be uploaded in the robotic controller, and the state server description and the main program. The state server is actually running the whole time on most robotic brands. The robot state server, so the other communication channel, the first one where the Picking Studio is the server, that is used for the robot to send the requests. So for the to initialize the vision system, to trigger a scan, to get a trajectory, and so on. And the second communication channel, where the robot creates a server, the state server, and it is used to provide the vision controller with the current state of the robot. This robot state server is used for, I was mentioning, for several stuff, several things. So it is needed for calibration procedure, because when we are doing the calibration, we need to know what is the position of the robot in relation to the sorry. Can you still see the presentation? If you could please give me feedback in the chat. Thank you. Okay, so for the calibration, because we need to know the relative position of the scanner and the robot, we need the current robot state during the hand-eye beam picking, because we need to know what is the actual position of the scanner. And since it is dependent on the position of the robot, we need to know where is the robot. And we need also for this data from the robot state server for the real-time visualization in beam picking studio, which is always nice to have. Okay, so the configuration of the tool, as I was saying, so the CAD model, the indicator tool point, whether the gripper already has a tool point defined. So we need to have selected tool point to have a full configuration of the gripper. And we already done all this, and we talked about the symmetries. So one more time, maybe, as you can see, this object is cylindrical, it is symmetrical around its long axis, and we can leverage that because we need to tell the system that here is the part or here is the gripper, and it does not matter whether this part or the gripper is rotated around the axis of symmetry, because it is always the same. Okay. And now, after the tool has been configured, I think I forgot to select it because there is one more thing. So I'm going to save it. Yes, gripper, and our new gripper is here. So just select, and let's talk about the picked objects. So the picked objects, or the parts that we are picking, we can upload up to 4 parts. We can have also up to 4 vision systems. Later on, a part is also, as the gripper, defined by a CAD model. Each part is then assigned to a vision system, and the part itself, the model is used for visualization, for definition of the points where the gripper will be picking the object. Also, this model is used for configuration of the localization. And also, one more thing, a part is also a collision object in 2 ways. Firstly, it is a collision object after it is localized. So not only the point cloud is the collision object, but to have more data, we also use the whole collision of a whole model of the part as a collision object, and when the part is picked in some in some moment after the picking, the part is attached to the gripper during the collision checking. So from some point in path planning, the part is considered as part of the kinematic chain, so the robot, gripper, and the picked object that cannot collide with each other and also with the environment. So we are doing path planning and collision checking also with the picked object, so we navigate safely from the bin and to the target destination. Okay, this is very similar the process of defining a picked object to the definition of gripper. So you just upload the STL. Also, the volumetric model is generated. And I would like to stress one thing: always keep the models as small as possible. That is sometimes not entirely possible to have a few kilobytes for the model of gripper, but the simpler the model, the faster the collision checking, because when there are a lot of faces in the STL, the collision checking will take longer. And this is mainly important for the picked object. So there will be a warning in the bin picking studio if the object is too big, but keep in mind that the lower the better. The object needs to have some details, some amount of details for the localization to work properly, but the bin picking studio does not need some very complex models, especially for the environment that will be defined later on. And one thing to, you can see the warning here, so that this model is too big and it is not much of a benefit. And you can also see that the normals in this STL model are not correct. The model is not close, so it is corrupted model basically. You should check, you should keep an eye out for this. The STL must be correct. Okay, let's define our picked object. And when I say picked object, I mean both of them, because we will be picking two different objects today. So the first one will be cylindrical object, or we can put simply cylinder. Okay. Let's check. Yes, this is the model of the object. It is not perfect cylinder. There are some holes on the side, but right now we don't care about that. And that is all. Once again, this other object is a cogwheel. Both these parts are metal, so we will be using the metal gripper, magnetic gripper, sorry. Okay, so you can see that the model is not very complex. You can see that it is not perfect, but it is totally okay for bin picking, for the localization, for everything in the bin picking studio. And now let's go to the definition of gripping points. Let's get back to the presentation for a while. There is a question. Can you train from several point cloud images of the object instead of CAD? Not right now. Right now, only the CAD file and the STL format specifically. is required to define a part? Thank you for the question. Okay, so the definition of the gripping points. Sorry, so the gripping points, this is the definition of the grasp. So how the gripper will grasp the object, where it will be on the object, where is the point of contact between the gripper and the part. There is another question. How did you add two picked objects? So I'm still on the picked object page. Just click the picked object, and there is the add picked object button until you reach the limit of the fourth object, of the 4 objects. So I have 2 right now. I can add 2 more. After I add 2 more, I won't be able to add more objects. So just click add picked object, and you can define another. Okay, let's go to the gripping points. So you can have several gripping points for each object. You should define a gripping point for all orientations of the object, of the part, because when you define gripping point from only one side and the part is lying on the other side, naturally you won't be able to pick the part until it moves, or in this case it rotates, which might not happen. That all depends on your application. Sometimes you want to define only several gripping points and then maybe use another strategy. Each gripping point can be disabled. That is mostly useful for teaching oriented placing. We will be talking about oriented placing in a short while. I am going to basically skip this and go straight to the definition. This is very similar to the definition of tool point. Again, we can see that up until now it is just working with the CAD files and in these visualizers, defining some points on the models. So nothing really, nothing difficult. No special skills required. Okay, so let's go to the gripping points. I have 2 gripping points, so I need to choose. I have 2 picked objects, sorry. I need to choose for which I'm going to define a gripping point. So let's select the cylindrical part as first. Unique ID, pre-generated 1. Okay, add new gripping point. The gripper, or more specifically, the tool point is automatically positioned in the origin of the CAD file of the part. I need to adjust it. When we look at this part, where is the area, where is the surface that can be used for picking with this gripper? Well, I see 2. So I'm going to be picking from side like this. I'm going to adjust the position. So this is a magnetic gripper, as I was saying. So we need to just slightly touch the surface of the part, and the magnet we'll do this. We'll do the rest of the stuff. Okay. Can be. And once again, we are in the moment where we need to think a little about the all possible configurations for picking. I enabled rotation invariance for the gripper. So the gripper can pick this part like this, and the gripper can also rotate. So there are 8 possibilities how to pick this part. But we need to tell the system that this part is symmetrical, is also symmetrical around its axis, because it does not matter whether the gripper will be here, or if I allow the invariance, the rotation invariance option, whether the gripper is picking from this side, this side, this side. So once again, using the enable rotation invariance option, we multiplied our gripping point, and right now we have 8 times 8, so 64 possibilities how to pick the part, because 8 for the rotation of the gripper and 8 for the rotation of the gripper around the part itself. You might think that that is a lot of combinations. It is, but when the part is localized, we definitely won't be able to pick from the bottom. So a lot of these combinations will be very fast rejected, very quickly, because they are under large angle. The gripper will be in large angle in respect to the z-axis of the world or the robot coordinate system. So basically, no path planning is done for these configurations that are not suitable. So not a lot of time is wasted. Once again, we could increase the number of rotation steps. I'm not going to do that right now. We will try with the default 8. Let's save. Let's also take a nice screenshot for a thumbnail. So when I go to the gripping points, I can preview it quickly. And let's add another. So I think there is one more option how to pick this part, and that is from the top, this bottom side, there is a hole, and the magnet will most likely not be able to pick the part from the side, but from this one, it might be possible. So let's just reorient the gripper. Let's round the value. This is a little bit too much. So there is a small gap between the gripper and the picked object. Okay, I could enable the rotation invariance here around the y-axis, but this is, if you think about it, this is the rotation that is defined for the gripper. So doing it here once again for the part, for the gripping point, would be totally redundant. You would end up with 64, again 8 times 8 combinations, but each 8 combinations would be the same. So this is totally incorrect. This is wasting of computation time of the resources of the vision controller. So we will not be using this invariance, because the gripper invariance, the tool point invariance, already takes care of that. So we have 8 possibilities how to pick the part from this side, because the gripper is invariant for rotation around the z-axis, around the tool point. So let's save. There is also the option to teach the gripping point here at the bottom. I'm not going to do that right now, but how it works is that instead of manually defining the gripping point on the model, you will teach it based on the actual grasp. So you take your robot, you attach the part as it should be attached during picking to the gripper, and then you just, after you have calibrated your vision system, naturally, you have just positioned the gripper with the part under the scanner. This needs to be done with extrinsic vision system, so not with hand eye. You need to have the scanner mounted above the bin. And once positioned, the gripper and the part under the scanner, you take a scan of the scene. The part will be localized and the gripping point will be calculated, because since we have calibrated vision system, we know where the part is in relation to the robot. So in the robot space, we know where the tool point is, so we know where the gripping point is. This is especially good in cases when you have a model that is not so, let's say, symmetrical or so easy to work with. But for these simple parts, this is much faster and totally okay. Okay, let's save. And let's talk about one more thing. I'm going to add one more picked object just to demonstrate some more options during the definition of gripping points and invariances. So this will be object 3. And I'm going to upload. Can we set, there is a question. Can we set multiple axis invariance in the picked object? No, you cannot set multiple axes, but you can have multiple gripping points, and each gripping point can have different axes of symmetry. So basically, all use cases I could think of are covered with the options that the Beam Picking Studio provides. I hope I answered your question. If you had something else in mind, please ask again. Thank you. Sorry, I muted my microphone because the compressor was working. The magnetic gripper is actually operated by compressed air. So from time to time, the air needs to be compressed. Okay, so this is third object, and just for the demonstration of some other options during definition of gripping points, I'm going to first I'm going to add the gripping points for the other part that we will be using. So for the cogwheel, let's rotate the gripper. This can be picked only from the bottom or from the top, so 180 degrees. Let's get it a little bit closer. There's the arrow, something like this. Maybe even like this, okay. And once again, the gripper is or the tool point is symmetrical. So these are 8 options how to pick the part. But from the bottom side, I can create another gripping point, or I can simply enable rotation invariance. But this time, let's change some things. I only need 2 configuration steps because one is from the top, one is from the bottom. I need correct axis. So for example, X. And right now it looks like this. So from the top, it's okay. From the bottom, it's not, because the axis is not going through the correct place in the part. So I'm going to put it in the middle. And now when I change the invariance, you can see that it is correct. But there is still slight overlap between the part and the object. And we don't want to crash into the object during picking, so I'm going to put the axis a little bit lower. Yes, something like this. So this is the bottom side, and this is the top side. Let's save, and we have 2 gripping points for the cylinder object, and for the other object we have 1 gripping point. This object has 1 gripping point with 2 invariances times 8 for the gripper invariances. So there are 16 possibilities how to pick the part. Here we have 8 times 8, so 64, plus there is no invariance for the second gripping point, so the 8 options thanks to the gripper invariance. So totally here are 72, 64 plus 8, 72 configurations, possibilities how to pick the part, and for this we have 16. What is most important, we basically covered all orientations in the bin. Well, maybe not entirely, because this part can be oriented this side up in the bin, and that will be a problem. But there's basically nothing we can do about it right now. We will need to hope that the parts will be shifted a little bit, will be moved during the picking, and they will change their orientation, or there are some other options how to change position, orientation of the parts in the bin. Okay, let's get back to the gripping points, and let's check the third object I uploaded. So this is a classic tail fitting, and what I wanted to show you is the limitation of the invariance of the range of invariance rotation. So let's, for the sake of this demonstration, let's say that we can pick the object from the sides, from all 3 sides, even though there are holes in them in the object. Okay, and I'm going to enable rotation invariance. I'm going to select the correct axis, so for example X, and you can see that the gripper can pick the object from all these sides. Well, this is not correct. Obviously, I need to get rid of the incorrect in suitable positions, and there are several ways. I can either disable these invariances, so the only that are suitable are the 0. Here is the number, the 0, the second, and the 4th. So I could do something like this, and I have basically gripping point with 3 invariances. So I have 3 options how to pick the part, or I can put 4 in here, so there will be fewer steps, and I have only 1 that is incorrect. So I can just disable the last one. So these first three will be used, that these are correct, and this one won't be used. Or the most perfect way is to limit the rotation limit. So the lower limit is 0 and the upper will be 180. And in this case, I only need 2 rotation steps. And you can see that I have 3 invariances, and those are the correct positions. I can save, even though I won't be using this object. I can also duplicate a gripping point. So let's duplicate it, let's edit it, and similarly to the first gripping point for this object, we could also grasp the part like this. So from this side. And now when we enable rotation invariance, it should go through the z-axis, and similarly to the cylinder object, we can go around the part. With the default options, it would be 8 steps without limit on the symmetry. So it would be like this. Once again, this is not correct. This is a collision between the gripper and the picked object. That would actually be rejected, but we don't want to even consider this. So once again, we can limit the rotation range, and we can only have invariances from this side of the object. So there's plenty of options when defining gripping points, and that's basically what I wanted to show you. You just need to think about all the possibilities and define them. Okay, let's save. Even though this object won't be used, it doesn't matter. It can be here. If I, for example, decide I want to use this object, I have less work to do. Let's check the Q&A. Okay, we are all good. And let's get to the presentation once again. Okay, I was talking about the teaching of the gripping point, which is an option. I have some notes with me I wanted to mention, so I'm just checking them. Okay, let's talk about one more thing, even though we will get to it later, and that is the oriented placing. There is a small chapter in the documentation for the oriented placing. It's pretty simple. BIM Picking Studio does not do the placing, but we provide data for the oriented placing. So when you go to the oriented placing, it's under the robot module. There are 3 numbers which fully define how the object was picked. And these 3 numbers are the invariance of the tool, which we have already configured. Then it is the gripping point ID. We have several of these gripping points. And there is the gripping point invariance. And once again, we define some invariances for our gripping points. What that means is that when a part is chosen to be picked and robot requests a trajectory for this part to be sent to the to the robotic controller, together with the trajectory, these 3 numbers which define which invariance of the tool, which gripping point, and which invariance of the gripping point has been used for picking. And since the robot knows which configuration of these three numbers was used for picking, we can teach placing positions, because when these three numbers are repeating, the object is picked the same way. So when I'm using the first invariance of the tool, I'm using the first gripping point, and I'm using the first invariance of the gripping point, the object will be grasped the same way in the gripper as when the next time the same configuration is used. So I need to teach a placing position for all these configurations. You might ask, well, there is a lot of configurations. I was talking about 72 for the first picked object and 16 for the second picked object. But since the objects are symmetrical, we do not care about the invariance of the gripping point, and sometimes even we don't care about the invariance of the gripper of the tool. So for this object, for this cylinder object, it does not matter whether I pick the object from which side I picked it, it's the same. So the only thing that I need to differentiate is basically the invariance of the tool and the gripping point ID. So whether it was picked from the side or it was picked by the other gripping point, by this one. And it all also depends on what is your placing routine. So whether you are placing on some kind of station, or you are just or you are using some helping helping machine for placing. So basically, you need to just in most cases you just need to define several basic placing positions, and that is all that is needed. Or you can make use of the offsetting functions on the robotic controller. So you just teach one position, and then when you know that you have 8 invariances, you will offset by 45 degrees each next placing position. So you just need a little bit skill with the robotic programming, and you can teach the placing positions pretty easily. So this is regarding the oriented placing. And one thing to help oriented placing is the disabling of the gripping points and the invariances, because once you have usually you do this the way that you receive a trajectory, you actually pick the part, you stop the program, the robotic program, and you teach the placing position. And once you have taught this placing position, you don't want the system, the beam picking studio, to send you the same configuration because it was already taught. So you just stop when you start to get the repeating configurations, you just go to the gripping point or the tool point section, and you can disable the invariances you have already taught, and the system will calculate the trajectories for the rest of them, and you can teach those positions. Once you taught all that is needed, you have achieved oriented placing. There is one more option, that is the priority of the gripping points. This is a little bit confusing sometimes for the users, so I like to stress what this means. There are 3 levels: low, normal, and high. And what this means is that when I select for this gripping point to have high priority, it means that the system will try to calculate the trajectory for this gripping point or its one of its invariants as first. So when there is another gripping point which has lower priority, this gripping point with lower priority will be considered only after none of these invariances with high priority are not possible to have trajectory calculated. So invariances with high priority are considered first, and then the other with lower, with normal and low priority. Okay, thank you, Eric, for specifying. So you meant a cube where you have multiple symmetries. No, as I already told, there is no option to define multiple symmetries, but for the cube, maybe I would go with slightly different approach, and that is definition of only a part of the picked object, so only maybe the top face of the cube. So basically the cube will be always localized the same way. So because when you scan from the top, you will scan only the top face of the cube, and then you only need to define one single gripping point for the single face. So that's also an option. Or you just define gripping points for all faces, and no matter how the object is localized, there will be a gripping point for it. Thank you. Thank you for the question. It was a good question. Okay, let's get back to the presentation. And now the grasping method. Well, let's first talk about what is the grasping method. And it is basically a blueprint for the beam picking trajectory. So for the unique trajectory that is calculated by Beam Picking Studio for the robot to execute to pick the part. And this blueprint consists of several waypoints. These waypoints, there are 5 of them. These 5 waypoints are mandatory, and we configure these waypoints to define the blueprint for the beam picking trajectory to ease the path planning, because with correct setup of the grasping method, we can have more successful path planning, much faster path planning, and so on. From the version 1.6 of the Beam Picking Studio, there is option to define multiple grasping methods, because a grasping method is highly dependent on the definition of the tool point, on the definition of gripping points, and also it depends what is the part, when you are using multiple parts, each part might be different, of different shape, each part might be in a different bin, and each bin might have different shape, what I meant to say, and this might require different grasping methods, so different strategy for picking, and using multiple grasping methods allows you that. A grasping method is then associated with a vision system. We will get to vision system after the grasping method. Okay, so the grasping method consists of several waypoints. The 5 are mandatory, the basic 5. So these are the start waypoint, the approach waypoint, the grasp waypoint, so where the picking actually takes place, the approach waypoint, and the end waypoint. You can add new ones if necessary. Sometimes it is necessary, and there can be up to 11 waypoints, but I think 7 is the maximum I ever saw. And the waypoint, so it is a point in space, right? And it can be defined in relation to different things, and we will be talking about that right now. And then what is a trajectory? The trajectory is a sequence of points that joins two consecutive waypoints. So each beam picking trajectory, when I say beam picking trajectory, I mean the whole trajectory that is computed for the robot. And this trajectory basically consists of small trajectories or segments of trajectory between individual waypoints. So when I have 5 waypoints, there are 4 trajectories between them. You can define whether these trajectories are joint type or whether the robot should move between these waypoints in linear path. One note between the approach and the approach waypoint. So from the 2nd to the 4th waypoint, the trajectory is always linear. And now let's talk about the individual waypoints. So there is the start one. I already mentioned that after connecting from the robotic controller to the vision controller, the first thing to do is to initialize a vision system. What it means is that each vision system needs to know where is the starting and where is the ending point of the beam picking trajectory. And this point is actually usually above the beam, just above the center of the beam. In most cases, the start and end are the same points, or sometimes the end is moved towards the placing position slightly, but you should always try to keep the trajectories as short as possible, so the trajectories are computed more quickly. It's also an easier job for the path planner, and basically there is no reason to calculate trajectory, unique trajectory for in the space where the robot can do pre-programmed movements, so where there is no collision, when there is no risk of collision. So the only place where there is a risk of collision and we need to do the beam picking is in the beam or in the area around the beam and above it. But when we pick the object and retreat with the object from the beam, from then we can program all trajectories on the robotic controller. The trajectories will be always the same. There is no need to plan them with path planner. So always try to keep the trajectories as short as possible. So only from above the beam to the part, and with the part to the end position above the beam, and that's all. In each waypoint, there is an option to call a procedure, and what that means is that in each waypoint, a gripper command can be executed. So a procedure for the gripper to do something does not actually need to be the gripper, but the robot module contains empty definitions of several functions, and one of these functions, you can choose it in each waypoint to be executed, and the robotic programmer just fills the empty definition of the procedure on the robotic controller with the appropriate command that should be executed in, and this is basically in most cases needed just for the grasp waypoint where you want to activate the gripper. So for the grasp waypoint, we will get to it in a while. Let's go to the approach first. The approach waypoint, this is the waypoint where the gripper orients, rotates and reorients so that it can grasp the part properly. This waypoint is relative to the grasp waypoint. So the grasp waypoint is provided to us by a localization, and based on the position and orientation of the localized part, we have defined our gripping point. So we know where the tool point should arrive during the grasping. And when we know where the grasp is, we need to have a waypoint just a few centimeters shifted from the grasp waypoint, where the gripper will take the correct orientation and it will just move linearly to the part and grasp it. There are two strategies available. So the approach can be relative to the found gripping point, which is the option I was describing right now, or it can be in the robot coordinate system, which means that basically the gripper would be positioned with the orientation of the orientation will be gained from the orientation of the grasp waypoint, but it will be exactly above, because the robot is in usual case, it is mounted vertically. So the z-axis of the robot space, of the robot coordinate system, points upwards. So the approach would be exactly above the grasp waypoint, and the gripper would, during the execution of trajectory from the approach to the grasp waypoint, the gripper would be executing a linear path downwards. I will show you, we will look at this in the visualizer so we can see better what I mean. This is a little bit harder to describe by words. This is the relative offset found gripping point, but I think it can be better visualized in the beam picking studio. And this is the robot, and let's go directly to the grasp. So I was saying that this is provided by the localization. You can see in the bottom right corner the visualization of the basically movement from the approach waypoint to the grasp waypoint. So the gripper is in correct orientation, and the coordinate system of the part of the gripping point and the tool point overlap. And in that moment, the procedure name, you can see that there is a procedure selected and the procedure is attached. So in that moment, the gripper is activated. In the moment when the grasp waypoint is reached. Then there is the approach waypoint, again, very similar to the approach, and this is the waypoint where to which we need to retreat with the picked part from the grasp. So we grasp the part in the grasp waypoint, and we need to go to another waypoint. Also, this is a linear path, and in the approach waypoint, the picked part is actually attached in the system, in the beam picking studio, to the gripper. So from the approach waypoint, we are doing path planning and collision checking with the picked part. There are some more options how to define the origin of the relative offset for the approach. So not just the robot base and found gripping point, which are available for the approach waypoint, but there is also option to go to a fixed plane or to define the approach relative to the start waypoint or to end waypoint, which have many great use cases. So I will show it to you in a moment. We can check these nice GIFs. So you can see that in the found gripping point, the gripper is moving in direction of the found gripping point, and the found gripping point was found, or the used gripping point that was chosen for path planning is rotated slightly towards the origin of the relative offset is set to robot. You can see that the robot goes to the up to downwards, and the waypoint that is defined to have origin of the relative offset fixed plane, the waypoint will be always in the same height. So it does not matter whether the grasped waypoint was at the bottom of the bin, so the part was at the bottom of the bin, or at the top of the bin, the approach will be always at the same height. So for the lower parts, for the parts at the bottom of the bin, the approach trajectory from the grasp to the approach waypoint will be actually a lot longer than for part that is at the top of the bin, which will be much shorter. Okay, let's skip this and let's get to the bin picking studio where we can see better what I was talking about. And then we have the vision system. Okay, you can see that the grasping method does not have a check mark next to it because there is always one default grasping method. It's called basic grasping method. It's the most basic one, literally. It is currently not used in any vision system because there is none vision system right now. So let's check the default. So quickly, the start waypoint, nothing to do here. We can maybe deactivate the gripper just to be sure that there is nothing picked in the gripper, so the magnet will be deactivated. In the approach, the standard way to approach the part is in found gripping point, and we have the waypoint 100 millimeters away from the grasp waypoint. So this is in relation to the previous waypoint from the when I say from the previous waypoint, I don't mean start, but everything is dependent on the grasp waypoint. So previous waypoint in direction from the grasp. So the previous waypoint to approach is the grasp waypoint, and to the approach also the grasp waypoint. It's like a tree, it's going both ways. So the grasp is done. It is defined by the localization and the gripping points. The end and the start are provided by the robotic controller. So they are sent from the robotic controller during the initialization request that is sent at the start of the application, and the approach waypoint is in the basic grasping method defined as found gripping point. So origin is found gripping point and 100 millimeters. We don't want to plan linear trajectory from the start waypoint to the approach. We will go with joint trajectory. We have position tolerance, which is approximative, which means that the trajectory will blend to the other one, to the next one, and no procedure to be executed here. In the grasp waypoint, you can see that we need to go linearly. There needs to be a linear path from the approach to the grasp waypoint that is forced. Also, the position tolerance is precise. We want to go directly to the gripping point, exactly to the gripping point. We need to reach that point with perfectly. We don't want to approximate the movement. The procedure to be executed here is attached, so the gripper should be activated. So right now we have actually grasped the part and we need to retreat with it. So we have the approach waypoint. The most natural way, the least colliding way to go with the picked part to the approach waypoint is to go basically upwards, directly upwards. So we can use the robot as the origin of the relative offset. Again, let's go 100 millimeters. Again, let's go we must go in a linear path, and we can have approximative position tolerance. We don't want to execute any procedure for the gripper. And in the end waypoint, which is again defined by on the robotic controller and transferred in the request to initialize vision system, we just can select plan linear trajectory, but we don't need to. We will use joint trajectory. And again, we can approximate the movement and do not execute a gripper command. Okay, so this is the grasping method. We didn't change anything. It was not needed. We only defined the procedures for the gripper. But let's check the options, the other options for the D-approach and approach. So these are the 5 options that I mentioned earlier. And I have some solutions for that. So let's check this one first. Okay, I started the beam picking solution because this is fully configured solution. I can do that. I started it in a simulation mode, so I will be actually the one that will be calling the request, not the robot. I need to initialize my vision system. I'm going to choose a proper start and end position, something like this. The same for the end. We will talk about the simulation mode later. I just want you to see the different options. So I have 2 vision systems, and both vision systems use different grasping method. Let's check the correct approach. I didn't initialize the second vision system. Okay, so this is the correct one. And in this case, I'm actually using a 2-finger gripper, and I want to put the fingers in the hole and open the fingers. Okay, so I'm not closing the fingers, I'm opening the fingers. What I need to do, naturally, in this case, I need to go in the found gripping point. You see, so the gripping point, as we were defining it a few minutes back, the gripping point is on the top side of this part and on the bottom side of this part. And you can see that the part is oriented, it is not facing, it is not lying on the bottom on its face, it is slightly under some angle. And the found gripping point is then in the z-axis of this gripping point. So it is 100 millimeters in the direction of found gripping point. And I need to use this found gripping point offset, because if I used the robot offset, this is the robot offset, so this is used for the approach. So this is the approach waypoint. I'm going in found gripping point. In the grasp waypoint, I grasp the part, and now I am doing the approach trajectory in the robot space. So this is the default option basically. But if I switch these approaches, so I would have approach in robot in relation to robot and the approach in found gripping point. I can do that, and for magnetic gripper it's basically not bad. You can see that it's the same, but right now, the gripper will be going downwards. And since I need to put the fingers of the gripper inside the hole of the part, I'm colliding with the part. So this is why we need to, in some cases, use the fan gripping point, because it is the only option. If this was the magnetic gripper, I could come from the top downwards, but still in direction of fan gripping point, it is the most logical in most situations. It is the most suitable way to approach the part. Actually, Beam Picking Studio would reject this trajectory because it is colliding with the part, but I allowed the volume of the gripper to collide, high amount of the volume of the gripper to collide, to show you this. Okay, so fan gripping point, and this is the robot offset. And then there are the three other options. Basically two: the fixed plane and the approach in relation to the start or end waypoint. Since the start and end waypoint are the same, we can consider it the same. So this is another example. Let's initialize the vision systems. Too much. Okay, so I want to be above the center of the bin, like this. The same for the end. I'm going to copy these values and use the same ones for the other vision systems. Okay, and let's check the first one. So let's check the fixed plane offset. I'm going to log out from the other scanners. And I'm going to hide the front wall of the bin. It is very deep, so we can see clearly what is happening. Okay, so I was mentioning that with fixed plane, the approach waypoint will be always in the same height. So when I select this part, you can see that the trajectories are really, really short. We are going from start to approach 100 millimeters above the grasp waypoint in the direction of fan gripping point. I'm going to grasp waypoint, and now I'm going to fixed plane, which is actually for this defined 150 millimeters above the robot base. So you can see that here is the robot coordinate system. Let's show the axis. Okay, so this is the robot coordinate system, and I'm 150 millimeters above in the D approach waypoint. If I select a part that is at the bottom of the bin, if I had chosen the robot offset, so I would go 100 millimeters above the grasp waypoint, as is configured in the basic grasping method, I would not leave the bin. And with part as big as this one, that would mean I would probably collide. Well, I would not collide with the part because the part is considered as a collision object. So the path planner would actually try to find a trajectory to go outside of the bin, but it would be a pretty difficult task because the part is very big or the bin is very small. So it might fail, the path planner might fail, or it might take a while to find the trajectory. But in this case, when I have a fixed plane for the approach that is above the beam, I'm sure that for all parts, the approach waypoint will be always above the beam, above the upper edge of the beam. So I solve this issue. The same goes for this one. Then there was the option to have the approach in relation to start a beneficial in case I actually have a lot of stuff running currently. So I need to restart. So why is the D approach in relation to start or end beneficial? Because I can use this start or end waypoint to define the D approach to be leaned toward these waypoints, and that means away from the walls of the beam. Because sometimes you need to go away from the walls of the beam very fast in order not to collide. You can see that for this one we failed because this is actually too long a trajectory, because I defined for the D approach to be half a meter long trajectory, 50 centimeters. And so let's check it. I'm in start waypoint. I'm going to my approach, which is still 100 millimeters above the part, above the grasp waypoint. I'm in grasp, and now I have the D approach in relation to start waypoint. My start waypoint is about the center of the beam. I defined for the trajectory to be 50 centimeters long. So I'm going away from the beam, from the walls of the beam. I can also not go directly towards the start waypoint, but I can offset this waypoint to be slightly in a different position. So if I wanted this trajectory to not be under such a high angle, I could define the point towards which I want to go a little higher than the start waypoint. So I would go to the solution. And here I have the 50 centimeters, 500 millimeters, and I'm going towards start, but I can offset it. So if I put, for example, 1 meter here, I would be actually going towards point that is something like in the height of the scanner. So you can see that the angle would be a little smaller. So the part would go still away from the walls of the beam, but not so fast. But for this part, this is not suitable because 150 centimeters is too long trajectory, and this is probably outside of the robot's reach. Yes, this is unreachable, but I can combine these approaches to solve this issue. So right now, you can see that I'm once again going to approach to grasp waypoint, then I'm going towards the start waypoint, but only 150 millimeters, and then I'm using fixed plane to go up. So I am I'm going away from the wall of the bin to not risk any collision. And then I'm going to fix plane, and since it is also used for this part, the trajectory looks a little bit weird, but it's all good. I'm going from start to approach towards the start, and I'm just going downwards a bit to the fixed plane. I can define the fixed plane a little bit higher, and it will not be doing this, but it's no problem, basically. You can see that the trajectories are very short. And okay, so you can see that there are a lot of options how to define the approach or the approach of the in the grasping method, and you can solve basically all kinds of situations, and especially with different grasping method for each bin. With this second bin, where you can see that it is not very deep, the basic grasping method would be totally usable here, but for the deep bin, not so much. And when we have two vision systems or two bins, we can now define a optimal strategy for picking optimal grasping method for each vision system. So for both parts, for both bins. Because what is the vision system? We are getting to that right now. So let's get back to our solution and let's talk about vision systems. Our first thing, what is a vision system, finally? Vision system is a concept we came up with in version 1.2. And a vision system is basically, it ties together several things in a solution. So specifically, that is the scanner and the calibration of the vision system or the scanner. Then it is the picked object. So one of those we defined. Then the localization profile. So the set of parameters for localizing the picked object. Then the mentioned grasping method, and also some settings that are unique for each vision system. And you can use up to 4 vision systems in each bin picking studio solution. So one solution is deployed to be running one application, but inside that application, you can operate 4 different scanners or 4 different parts and 4 different bins. You can combine these things and achieve a lot of stuff. When you think about it deeply, there is a lot of configuration options and a lot of use cases that can be done with vision systems. Then during the bin picking, I was already saying several times that the basic application consists of connecting to the vision controller from the robot, initializing the vision system with start and end pose for the path planning, and then in each cycle repeating scan request, so request to trigger a scan, and the scan is then followed by localization and path planning, and then request to for the vision controller for the bin picking studio to send the calculated trajectory to the robotic controller so it can execute it, so it can pick the object. And when you are calling these functions, you are actually calling specific vision system. So you can only use one vision system, or you can use 2 vision systems and switch between them in each cycle, or you can use one vision system for 10 cycles and then switch to another, whatever the application requires. Configuration of the vision system. So each vision system has a name that's just for you, so you can identify it. It has a unique ID, just like the solution, because it is used in the requests from the robot. It is associated with the scanner and its model. Model is selected because it is used as a collision object in the scene, and then you choose how is the scanner mounted. So we will be using 2 vision systems. We will be having scanner mounted on the robotic cell, so in a static stationary position, and also on the robotic arm. Based on the scanner mount position, the calibration procedure differs a little bit. And then we need to associate the correct, the part we want to pick, we want to localize and pick with this vision system. Then the grasping method. And the last two things are the localization profile. So here we configure the localization. So the set of parameters for localizing the provided CAD model of the part in the point cloud provided by the Foxy 3D scanner. And also there is the calibration matrix is stored in the vision system. So this is the calibration matrix is the output of the next step, which is the calibration. Then there are also some vision system settings. I was already talking about the vision system, about the gripper collision sensitivity. About the gripper collision sensitivity. So the amount of volume of the gripper that can be in collision with stuff around it. So with the point cloud, with the scanned point cloud of the scene, so other parts and other stuff. And also there is the fast scan. Fast scan is a way to optimize your cycle time. And I'm going to mention more about it, talk a little bit more about it when we get to it in the beam picking studio. So let's define our first vision system. Let's call it cylinder S. This vision system will be using the scanner mounted on the robotic arm. So this is the one. It is model M, so one of the smaller models. The picked object is cylinder. We will be using just the basic grasping method. No need to change anything right now, at least. And we can create the new localization profile. Okay, this is the interface for configuration of the localization. Right away, I am going to start locate, click the start locate, which will trigger localization. There's some stuff happening in the background, and okay, this is what the scanner sees. And since this is the hand-eye scanner, as I said, I need to position it better above the beam, because from this position, it cannot see the full beam, the whole beam. Let's try now. Okay, this is better. Okay, let's talk about the localization a little bit. On the right side, there is the list of localized objects. Each object has a unique ID. There is point cloud rendered in different colors. Basically, this is the result of segmentation. Segmentation is one of the first things to be done after the scan is taken. So we are localizing only on the segments of which are of the green, which are in shades of green color. So the gray parts of the point cloud are not taken into consideration, are not considered at all by the localization, because these segments are, for example, too big or too small or something else. We only localization only considers the segments that are in shades of green. You can always color the point cloud in different colors, but in here you want to use the segmentation image, because you want to know that the point cloud is segmented properly. There are some basic options like the timeout for localization. The smaller the better, so in order not to waste computation time of the vision controller, so I'm not going to put 25 seconds here when I know I want short cycle time. I need to account for the scanning time in here also, and then localization, maybe even something like 7 seconds will be okay in this application. Then there is overlap. 15 is pretty low. You can see that, for example, this part is mislocalized, it is shifted. So I'm going to increase the overlap to 60. For parts with nice 3D features, with curved surfaces, I'm going to use surfaces matching algorithm. Combined would be used when the object is clearly defined by its edges. And the clustering level, this means how many clusters, how much segments there will be. So if you notice that two segments or two parts are consisting of the same segment, you want to increase the clustering level so that one segment is broken into two smaller ones. Let's try now. Okay, still enough parts to choose from. There are also advanced settings. So in case you have troubles localizing with default settings, you can tweak these parameters, or you can always ask our support for assistance. I'm going to decrease this number because we have segmented, we have clusters on the point cloud, but the cluster that needs to be considered, I think each needs to have at least 500 points. And I don't think any of these clusters is bigger than 50,000. This way, I am not going to consider the bottom of the bin or the edges, only the scanned parts. Okay, for these purposes, I think it is sufficient. In the localization interface in here, you can see that the parts are rendered in two colors, blue and yellow. Basically, the yellow parts are takeable right away, or the localization considers them not occluded, and the blue ones means that they are occluded from the scanner's point of view, from the camera's point of view. So there is something about these parts, some other point cloud part of the point cloud is occluding them. One more thing I'm going to do is I'm going to enable a bounding box. I mentioned that we can configure the scanner to only to clip the point cloud, so to define a region of interest in the point cloud, and I can also do something similar in the localization. I can take this bounding box and tell the system that I only want to localize inside the volume of this box. So this is especially helpful when you're using one scanner and scanning a large area, for example, 2 bins, and in each bin you have the same type of part or very similar parts, and there you don't want to localize the parts in the other bin, only in the one bin. So if I move the bounding box like this, then the parts outside of it will not be localized at all. Okay, let's put it back. And I am satisfied with the result right now. So let's save the configuration. And quit localization. The lunch time is getting closer, and we will have a break in a few minutes. I think we can create the second vision system. One more thing I was mentioning, this is hand-eye vision system, so this should be robot flange. So let's create the second vision system. I can duplicate this one, but let's create this one from scratch because there is not many similarities. So this scanner is mounted above the cell. It is this one. It is model L. It is mounted on the robotic cell. I'm picking this part with this grasping method. Let's create a new localization profile. Let's move the robot outside of the scanning volume. Okay. And once again, let's try the default parameters right away. Pretty good. But I'm definitely going to do the same little tweaks. So I'm going to define a bounding box just to be sure. Okay, something like this. Let's start locate. And also decrease the timeout and increase the overlap. And I think that's all that's needed. Okay, it looks pretty good. I don't see any mislocalized part. So let's save configuration. And this way we have ready both vision systems aside from calibration. So we need to just calibrate both vision systems, and that will be it. Just one more thing that I want to say before we go for the lunch. There are those two settings. So the gripper collision sensitivity is unique for each vision system. So this is the volume of the gripper. Once again, this is the volume of the gripper that can collide with the point cloud. And there is the option to use fast scan for each vision system. And I mentioned that this is a way to optimize your cycle time. So what it does is that the full scan is not taken in each cycle or in each call of the scan request, but actually only each third scan is the full scan. And full scan, I mean, that is when the scanner actually captures the point cloud. The other two scans, so the first is the full scan, the point cloud is captured, and the second and third scan is only two-dimensional scan, so only texture image, so only this is captured, and it is compared with the texture image from the full scan. And based on these other settings, specifically based on each change threshold and changed pixels fraction threshold, the images are compared, and the parts that moved are forgotten because they are considered as taken, and the parts that are at the same place, they are kept. And how the system does this? It compares the values of pixels. So this is a black and white texture image, and through these parameters you can the basic settings, the default settings, the default values are optimal. But in case the system is forgetting parts that it shouldn't, or the system is remembering parts that were already picked, then these parameters needs to be tweaked a little bit. And there are two other parameters. So this is the frequency of the full scan. 3 is a good number. You need to keep in mind that you want to have the point cloud data, actual point cloud data, not old ones, not old point cloud, because the point cloud is used for collision checking. And the full scan is taken in each third scan, but also when fewer than 3 parts are localized. So when I localize only 2 parts from the texture image, then I will trigger full scan even if another fast scan should follow. So this is to always have some candidates for path planning. And this minimum ready to pick objects option means that if I don't have any, or in this case, if I have less than 1 part, so 0, ready for picking, the next scan will be always full scan, even if it should have been fast scan. This is because I always want to have some part in memory that is ready for picking. I don't want to wait for trajectory to be calculated. So I define the frequency, I define at least how many parts need to be localized in each fast scan. If fewer parts are localized, the full scan is triggered, and also in each cycle, how many parts that are pickable, that have trajectory computed for them, how many parts that are pickable there need to be for the fast scan to be taken and not full scan. Okay, so we have both vision systems prepared. All that's left to do is to calibrate them and then define the environment, and then we can deploy our beam picking solution and test with the real robot. Okay, so we paused just after configuration of the vision system of both our vision systems. There is one question. For picking two different parts, we must define two vision systems. Can we do that with just one scanner? I was talking about all the possibilities that the multiple vision systems and the things that they tied together, what kind of possibilities that gives us. And one thing is that you can use one scanner, but you can use this scanner in multiple vision systems. So when you have two different parts, you can scan them with a single scanner, but you will be using two different vision systems. And in each vision system, there will be a different part selected. So just like now, we have two parts, two vision systems, but we are using two scanners because one is mounted above the bin and the second is mounted on the robot itself. We could always use the same scanner for both vision systems. It's just that I wanted to demonstrate both approaches, so both the stationary scanner and the robot mounted on the robotic arm. Okay. Now that we have defined our vision systems, we just need to calibrate them to be able to use them. So let's go to the calibration page. And start with the presentation. Let's start with the presentation. So slideshow mode. We were talking about the vision system settings. We were configuring the cat-based localization. And we were talking a little about the parameters of localization, and we configured also bounding box. There is one feature called empty scene. This is a setting in the advanced section of the localization configuration. I did not actually use this feature, but I can tell you something more about it. So when a robot requests a new trajectory, there can be four types of responses. The first thing that can happen is that there is a trajectory calculated. So the path planning was successful for at least one part, and this part is selected, and the trajectory for this part is sent to the robotic controller. So this is the thing we want. We want to send the trajectory to the robotic controller. There are three more possibilities that can happen. Path planning can fail. So in this case, the robot will not get the trajectory. It will get an error code, so a specific number, or the path planning did not fail, but actually there was not even a part localized. So there is another specific number for this error. So no object was localized. And the fourth option that can happen is that there is actually no part in the bin. And to be able to tell that there is no part in the bin, we can allow the empty scene feature. We can maybe look at this in the vision system itself. So let's get back to this one and just quickly demonstrate the usage of this feature. So when I start localization in this bounding box, there is a certain number of points. I'm going to define the bounding box a little bit more precisely, accurately, because the best results can be achieved when the bounding box is perfect. So I'm not going to count edges. I'm going to exclude the edges of the bin. And also I'm going to try to exclude the bottom. So something like this. Okay, and now in this in the top panel of the visualizer, there is the scan option widget, and it tells me that the type of scan was full scan, so the whole point cloud was captured, and the size of the scene is there is 38,000 points. This is actually subsampled. There is a lot more points, but for the localization, it is subsampled. So something under 40,000 points, and I can now allow the empty scene feature, which is in the advanced settings, and I can define the threshold for number of points. And when the number of points is under this threshold, the robot will not get the no part found response, but it will get the empty scene response. So another specific error code. So it can, after request for a trajectory, the robot can either get a trajectory, successful trajectory, successfully computed trajectory, or it can get 3 errors: path planning failed, no object found, or empty scene. And based on the error, you can do different stuff in the robotic program. You can employ different logic. To know what number to put in this field, I will at first remove all parts from the bin. Okay, and let's check now. And you can see there is 3.5 thousand points. Okay, and let's try to put one part in the bin. So I need to, the part is too low. I need to adjust the bounding box. So it should be something like this. Okay, so for the single part, I have 2,000 points. When I remove the part, one more time, I have only under 400 points. So that means something between is, for example, 1,000. And now when I start localization, very quickly, I have response that the scene is empty. Localization finished prematurely. So in this case, when the bin is actually empty, the robot will get empty scene error code. And when I have at least one part, so I put the part back in the bin, one single part. And when there is one part, based on whether this part was localized, it was, so it won't get the no part found. The path planning can either fail or it can be successful, so the other response will be sent to the robotic controller. So this is the way how to use the empty scene feature. Okay, we can save the configuration. And And let's go finally to the calibration of our vision systems. Okay, so on the picture, you can see what is the calibration. In this case, what is the extrinsic calibration? So calibration of the scanner mounted stationary in a static position above the bin. So we need to find out the transformation metrics between the coordinate system of the camera, of the scanner, more specifically the camera unit in the scanner, and the robot space origin. And I was already talking about this because the parts are localized in the camera space. So we need to transform their poses, their positions and rotations to the coordinate system of the robot. So the robot can know where the parts are in relation to its origin. This is our setup basically. So we have one scanner above the bin and one on the robot. When we are talking about hand-eye calibration, the transformation we are looking for is between the camera unit and the robotic flange. For this reason, during the hand-eye calibration, there cannot be TCP configured on custom TCP configured on the robotic controller. We need to have the tool 0 reported from the robot by our robot state server. To be able to calibrate, we need to have the vision system configured. We already done that. And we also need to have the robot state server task running because we need to know the current state of the robot. Let's do the extrinsic calibration as first. So for the scanner mounted above the bin, for this type of calibration, we will be using a calibration ball. This is a ball like this. This tool is a part of a Photoneo. This is a part of the Photoneo bin picking studio package. This is actually a snooker ball. It can be any kind of ball provided that its surface is scannable. It looks good on the scan, so not very reflective, and it needs to have perfect surface. It must be very smooth. We can also use, for example, ping pong balls because they are cheap. You can get a ping pong ball anywhere in the world. The only other requirement is that you need to attach the ball behind the 6th joint or behind the last moving joint of the robot rigidly, so it cannot move. I am going to attach the ball using this clip to the gripper of the robot. During the calibration, even for the hand-eye, the tool center point cannot be changed. So during the whole calibration, the same tool must be used on the robot. Okay. During the calibration, we need to add several calibration points. So the robot will move through the space, and in each different pose, it will request, we will add a new calibration point. We want to jog the robot as much as possible to change the rotation of each joint as much as possible. The ball must be clearly visible. And of course, as I said already, the ball cannot move. Okay, let's do the calibration. So let's just click Start Calibration. We need to select the ball. We can provide radius for our custom ball, but I'm going to use this predefined snooker ball. Let's proceed. Since the Beam Picking Studio version 1.6, we introduced semi-automatic calibration, which means that I can add the calibration point manually by clicking Add Calibration Point here in the Beam Picking Studio, but now the robot itself can add a calibration point from the robotic program. So in the robot module, apart from the example programs for basic beam picking applications, we also provide a template for calibration. So you just you reteach the poses, the calibration poses of the robot, and basically you just run the program anytime you need to do a calibration. And when you need to do the calibration, you need to execute the calibration anytime the position of the scanner, the relative position of the scanner and the robot is changed, or something else happens. Someone maybe just accidentally touched the scanner, maybe some light conditions have changed drastically. Basically, anytime that something wrong seems to be happening, you just recalibrate the system to rule out any error, any issue connected to the calibration, because precise calibration is required for good beam picking. Okay, there is mandatory 9 points that need to be added so we can calculate the calibration metrics. I have prepared the calibration program, so I just started the calibration in the Beam Picking Studio, and now I'm just going to run the calibration program on the robot and let the robot do all the stuff. So I'm just going to attach the ball to the gripper. Okay. Now, choosing the correct robotic program. Of course, one thing I forgot to do is to remove the bins. We want to calibrate in the volume of the bin where the beam picking will be taking place. So I remove the bin. Okay, so it's in the first position. We have first point added. You can see that the ball was recognized. We are in the beam picking studio. We are looking at the texture image with the ball highlighted with green color. In case of any error, there will be a error message on the screen to tell us what went wrong. For example, each calibration pose must be different. So there is, if the system recognizes that two calibration poses are too similar, the second reject the TCP by at least several centimeters and also by several degrees between each point. I'm going to go to verification tab where you can actually see the real-time visualization of the robot. And on my camera, you can see the actual robot. Okay, we have 7 points. In between the points, the robot actually goes to home position. And this is just for safety that all the calibration poses are collision-free, the movement between them, because we also have the hand-eye, the scanner on the robotic arm, so the movement is a little bit tricky. We need to be careful not to actually damage the gripper. Okay, this was the point number 9. And I think we actually have 10. After the 4th point has been added, the system is already able to calculate the system of equations, solution to which is the calibration matrix. So you can check the point cloud already after the 4th point has been added, but the 9 points is minimum in order to calibrate the system. I just got a little bit confused about the position of the hand-eye scanner, but this is because we were calibrating the extrinsic vision system. So the position of this small scanner on the robotic arm is not relevant right now. You can actually see it on the point cloud that the scanner is mounted elsewhere. What we want to do in the verification tab, okay, we have the calibration accuracy 0.65 millimeters, which is pretty good. We have accuracies for each point. Only one is about 1 millimeter. The last one, I think that is pretty good. If a point has a too high accuracies or too low, so the number is too high, you should remove it and add another point. It is possible, but it is possible that the ball moved or something. So sometimes you need to do the calibration again. So make sure that the ball is not moving after attaching it to the gripper. In the verification tab, we actually want to check the overlap between the model of the robot and the point cloud. And you can see that they are overlapping pretty good. You can also check the overlap with the gripper model, but the model might not be copy reality perfectly. So the model is for sure exact and precise. So you should check the model of the robot, not the gripper. Okay, I am satisfied with this calibration. You see that it was after I have prepared the program beforehand. I can do the calibration anytime, and it was pretty fast and easy process. So finish and save calibration. There is a question: are those 10 calibration points defined prior at the robot controller? Yes, I have prepared those calibration poses beforehand, not to waste time now. So that takes a few minutes, but you, as I mentioned, you have the template, the example program from in the robot module from Photoneo. So you just teach your own positions that are suitable for your robot and for your position of the scanner, because the ball must be always clearly visible. So you need to make sure that all poses are correct, and then you just save the program, save the poses, and run the calibration. Okay, now the same for the hand-eye vision system. For this, I am going to be using different calibration tool. We can go to the presentation for a while. So we did the extrinsic calibration and we did verification. And now we have the hand-eye approach. As I already said, the tool 0 must be selected. You will get a notification if it's not configured. on the robotic controller if there is a custom tool detected by the Beam Picking Studio. Here we will be using a different calibration tool, and this tool is called marker pattern. You can download it from Photoneo website, but it is also provided in the Beam Picking Studio package. And the principles are the same. Robot moves through different poses and scans the pattern. You can see it in the picture. The pattern is lying basically in the bin, and at the bottom of the bin or in the middle. You need to position it in the bin and not move with it. And that's basically it. So let's calibrate our hand-eye vision system. And I'm going to put the calibration pattern in place. You can see in the image in the Beam Picking Studio that I'm using quite a big marker pattern. This is not the one that is provided in the Beam Picking Studio package. This is a different one, but it does not matter. So in the Beam Picking Studio, there is format A4. So nice compact marker pattern. Okay, the calibration has been started. I'm running the robotic program. And once again, we can just watch the robot execute the calibration. So the robot just moves through the space, and the scanner takes scans of the marker pattern from different viewpoints. Okay, and now after 6th point has been added, the system is able to calculate the calibration metrics. So for this type of calibration, 6 points are the minimum for the math to for the equations to be solvable. And from now on, the gripper is in actual position. So it seems that the calibration will be successful. We have 2 more points to be added. Now the last one. Okay, there is actually 10 points too. And now the robot positioned itself into one more pose, and in this pose, I'm going to trigger a scan. Again, a very similar accuracy, 0.6 millimeters. I'm going to go to verification, and I want to scan my robot. So the robot moved into this position, and I'm going to just click trigger scan in the Beam Picking Studio to get the scan of the robot base. And you can see once again that the scan is matching the reality. You can even see the calibration ball I was using previously. So this calibration result too is very good. So all that's left to do is to finish and save. But before, there are two questions. So they should more or less cover region where we want to detect the parts. Yes, you want to calibrate in the volume where there will be parts. So for the extrinsic calibration and hand-eye calibration, well, for the extrinsic calibration, the ball should move in the volume of the bin. I, in general, tend to choose these poses of the ball to be in each corner of the bin. So there are 8 corners, 4 at the bottom and 4 corners at the top of the bin, and 1 point in the middle. So that is 9. And for the hand eye, just put the marker pattern in the bin and just go through 9 poses, 9 different poses from all possible viewpoints. And where can we, another question, where can we find the calibration module for the robot? Is it in the documentation menu? The calibration module is, if we are talking about the procedure on the robot, about the robotic program, about the template, that is part of the robot module. So that is the part of the archive, zip archive, that we will provide you when you write us on the support. So you just need to tell us what version of Beam Picking Studio you are using and which robotic brand, and we will provide you with a robot module that contains the robot module. We will provide you with the robot module, and that contains the set of functions, the library for the communication with vision controller, and part of that module is also all the example programs for basic beam picking application, for beam picking application using 2 vision systems, and also example for beam picking where you change solutions from the robot. So you just deploy another solution directly from the robotic controller. The 4th example program is the calibration itself. Okay, this way, when I finish and save the result, I have successfully configured my Beam Picking Studio solution. This is basically, these are all the mandatory steps, but there are 2 more things. Well, at least the one that is necessary, and that is the environment. It is not required to define the environment, but since I have a lot of stuff around my robot that I certainly do not want to damage, to collide with, I need to define it. So when I go to the environment, I have the robot here. I have my 2 sensors, my 2 Foxy 3D scanners in here, because I selected correct models, and based on calibration, I can tell where the scanners are positioned. And now I need to add all that's necessary, all that's reachable by the robot in order to be safe, in order for the path planning to know about these collision objects and not collide with them. So in the environment, we are structured. We have 3 tabs. There is the scene tab, the robot tab, and the vision tab. Let's start with the scene tab. So there is the root link, the scene, and we can add another object. I can draw simple collision objects, or I can upload an STL. Once again, I forgot about the presentation, but I don't think there's anything that needs to be said. We will go through it all. So let's just add an STL, and as first we will add robot mount. So the metal thing that the robot is standing on, and it is type environment. There are 3 types of collision objects. They basically just differ in color for easier navigation. So this is environment. It is rendered in gray color. You can see that there is exclamation mark in the robot tab, which means that currently the scene is not saved. So the robot and the jogging options on the robot page are not cannot be used because the scene is not synchronized with the rest of the application. Okay, let's add another STL. This time we will add bin. We actually have two bins, so bin right, in this type bin, of course. And you can see that it is under robot base. So bin picking studio supports hierarchy. So I can now move the robot base if I want to. I can move the robot base and the bin will move to together with its parent object. So the bin is currently the child of the robot base, and you can use this to manipulate group of objects at once. And another bin, so add child object, and let's add another STL, so bin left, type bin, upload. Let's select the bins and move them in approximate positions, something like this. Okay, and now that I have calibrated my vision systems, I can go to Vision tab and I can connect to my vision systems. In this case, I'm going to use this one, and I'm going to remove the marker pattern so I can see my bins clearly. And I'm going to trigger a new scan. I'm going to connect to this scanner and trigger a new scan. And since the vision system is calibrated, I can use the point cloud to fine-tune the position of my bins. So I can once again use either arrows in the visualizer and these markers, or I can fill in the form if I know the exact positions. So this has been left from the point of view of the robot, and the bin, another bin. It's on the right side. Okay, so the approximate position is like this. Let's save the scene. There is also the construction that is holding the scanner, and I certainly don't want to touch that. So I'm going to add another object, but this time I'm going to draw it. So I'm going to select box type, box shape, and I'm going to resize it. And it's something like, I'm going to make it a lot bigger, just in case. Okay, this is scanner mount, for example. And I'm also going to, select environment type, and I'm also going to add walls for my robot. So I'm going to enclose the whole robot in a box, and this box will act as walls of the entire cell. So I need to also have bins in the box, and I want to have the robots in the box. not the entire robot. During path planning, it will be above the bins, so safety walls. And this is virtual collision object. That means that the walls will be transparent. Okay, this is basically it. We have defined our environment. Let's check the robot tab. There are several things to mention here. The first thing is there are several motion modes we can try. So I can move with this virtual model by joints. I can also use in tool coordinate system, and I can also move linearly in linear paths in robot coordinate system. Now, I can highlight collisions, so the collision checking can be turned on. You can see that I'm going to hide the walls entirely. You can see, or I can also grab this ball, which is the tool point, and I can move my robot through the environment. You can see that all links that are colliding are being highlighted. Okay, so you can play with this a little, but what I surely want to do is I want to see my workspace, and it is quite big. I certainly do not want the path planning to take place in such a big volume of space that it is not at all needed. We only want to do the path planning in the bins and above the bins. So what am I going to do is I'm going to define joint limits. So I'm going to select some optimal values. I'd like to do this with using the joint jogging option. Okay, so on the first joint, we really don't need to go more than some 0.7 radians and minus the same. And this is the most important, the first joint, because it limits the motion of the robot the most. And then the second and third joint. So I need to be able to do something like this. So 0 is good, 0 is good, and 1/8. And for the third joint, minus 2.4, and for example, 0. Okay, let's save this work in progress. There is a question. These joint limits are just for the picking path or the overlap with the robot limits defined in the robotic controller? Good question. This is strictly for the bin picking studio, so for the path planning. This has nothing to do with the software limits or hardware limits of the robot itself. So if you want to actually limit the movement of the robot, you can do that. The entire movements of the robot, you can do that on the robotic controller. But this is just software limitation for the path planning on the bin picking studio side. So this does not limit the movement of the real robot. It just limits where the path planning will take place. So you can be sure that the calculated trajectory won't be outside of these joint limits, or even outside the safety box. Those are two limitations that we employ for safety reasons, and also to make the pathfinding more successful. Okay, on the fourth joint, we just need to rotate 90 degrees so something like minus 1.6 radians, and the same on the other side. We do not need to limit the fifth joint, and the sixth does not need to rotate so much. Something over 1 rotation to each side. Okay, let's save and let's check the working volume after making these changes. Okay, so much smaller. You can see that the bin is still in the volume of the bin. So I'd say this is correct. We can try the jogging option. We can still move freely. We can even rotate to the sides. Okay. This is just a demo setup, so the bins are not in the most optimal positions in relation to the robot, but it should be all good. Okay, this is all from the environment. I'm going to check the presentation in case I forgot something. So we defined our collision objects. We defined our joint limits. We tried jogging. We generated our working space. We used point cloud for fine-tuning of the position of the collision objects, mainly the bins. And now we go finally to the good stuff. Well, I think all of stuff here was pretty interesting, but now we can finally go to the deployment. I'm going to stay in the presentation for a little while. Once again, I'm going to mention one thing, that we created virtual environment. We uploaded some STLs, and as I was previously saying, let's keep the size of the environment models or models in the bin picking studio, the CAD files, the STLs, as small as possible. When I created the simple shapes, the box for the safety walls and the safety for the scanner mount, those are just plain boxes, and they are very simple objects. So the collision checking with such objects is very fast. So let's keep in mind that this is the best way to have fast collision checking, to not have very complex models, because there is no benefit in that in most cases. Okay, in the deployment, we from version 1.6, sorry, from version 1.6 of the bin picking studio, we are able to deploy a solution in 2 modes, in a simulation mode and in the production mode. So I'm going to choose the simulation mode as first. Maybe before, let's check the settings. No, let's do the deployment in the simulation mode as first. So in the simulation mode, the robot is not the master that is calling the requests. I, as operator of the bin picking studio, will be able to initialize vision systems, to call scan requests, and even requesting trajectory. So this is ideal for initial testing, because I don't need to do stuff with the robot, running the program and so on. We are on the deployment page. This is one of the first pictures that we saw in the presentation. Let's maybe talk a little bit about what we are seeing. So we are in the simulation mode. We can see that the bin picking client, that means the robotic program, that the main program that should do the bin picking, is disconnected. Even if it connected and requested any request, if it sent a request to initialize vision system, it would be rejected, because right now we are in the simulation, and for safety reasons, that is not allowed. We see that the robot state server is connected. So we are connected to the server, TCP server on the robot controller. And it provides us with current state of the robot. And you can see that this is the current state of the robot that is behind me. And then there is status of both vision systems, of scanners connected to these vision systems. So both scanners are connected. We are running beam picking studio training solution. We can stop it, restart it. Here is the interface for calling the requests in the simulation mode. We can monitor the cycle time. The cycle time is measured on the beam picking studio side, and it is measured between two following trajectory requests or scan requests. You can choose what should be shown. Two consecutive requests of the same type for the same vision system. So then you call trajectory request in each cycle for vision system 1, then this will be the time that passed between two of these requests. So between two requests for a new trajectory, for a new peak. Under the cycle time, there is the console where you can see messages about what has happened in the past. So right now we see that the deployment has been started, the Foxy 3D scanners connected to respective vision systems, and by that the solution was successfully deployed. In the visualizer, there is a lot of widgets. We can change the view. We can change the camera that is used, because there are two options, trackball and orbit. This trackball option gives you more free will, as I would say. You can hide. Yeah, you can hide any link, any collision object in the virtual environment, even the robot itself. You can show the axis of individual links. You can measure stuff, tweak the point cloud settings, visualization of the point cloud, check the scan properties, see the current joint states of the robot, and you can visualize the bounding boxes. So for example, bounding box for this vision system. Okay, I'm going to hide the vision system, the safety wall, so you can see better. And let's define some start position for our second vision system, so for the extrinsic one. The same for the end position. Let's send the initialization request. And now we can, for the first vision system, I cannot request the scan because I have not initialized the poses. So there is an error. But for the second, I can request a scan. The scan has been taken. The localization has started. I forgot to fill in the parts, so I have only one, and it is ready to pick. It is green color. Green means that the trajectory has been calculated successfully. You can see I can now use this. I can click on the part and I can open Inspector. Inspector is a debugging tool. It lets you preview all kind of stuff regarding the trajectory, regarding the path planning. So you can see for the fully calculated for trajectories that have been successfully computed, you can see the whole trajectory. You can preview it. You can change the representation of the gripper. So right now, I changed from the STL to the volumetric model. So this is the model that is used for collision checking in the grasp waypoint. So when the grasping is taking place, because there we need to, in most cases, allow some kind of collision. So a small volume of the gripper can be colliding. In this case, I mean the tip of the of the gripper. And we can see how much time passed for each trajectory, how much time it took for a path planning to be done. And also we can go through the configured waypoints. So we have start, we have approach, grasp, the approach, and end. Okay, let's add the remaining parts. Okay, and let's do another scan. There is a question. After a scan is made, is passed to robot controller, how many parts could be picked? After you take a scan, actually you can request all trajectories for all computed parts. So you can see here at the top there is a status bar. We have 21 localized objects and 12 of them are green, so pickable. 4 are bright red, which means that the waypoint computation failed. So that means that one of the configured waypoints, start and the approach grasp, one of these waypoints failed to be computed, and 5 parts, if we try to pick them, the gripper would collide more than allowed. So the volume of the gripper that is allowed to collide with the scan is exceeded. And I can request, and even the robot, after scan, all trajectories for all these green parts. So the robot could, in theory, request 12 trajectories, but you should not employ this logic. If you, well, sometimes it might be possible, of course, but let's imagine if I pick a part, so I request a new trajectory. So this is the first object to be picked. It is the highest, or based on the sorting criteria. I can then choose another and another, and you can see that the blue parts, those are the ones that have been already sent to the robotic controller. Well, but after each pick, it is possible that the parts in the bin moved, because based on the size of the bin, of the shape of the parts and how they are together, it might happen then when picking one part, others around it will move. And that will mean that when I request another trajectory, and the trajectory will be for the part that has moved, in the best case scenario, I will not pick the part, so it will be mispick, or in the worst case scenario, I will collide, so I can damage my gripper. For this reason, it is recommended to take scan in every single cycle. And if you don't want to do the full scan, you can always use the fast scan. So at least the fast scan should be done. So you can go to Vision System and allow the fast scan feature. Question regarding which is the system that decide when a new scan must be made, robot controller or bin picking studio? Always the robot is the master. So it is the robot that decides what should be done. So the robot requests a scan to be made, robot requests a trajectory to be sent, bin picking studio just serves these requests. So it listens to the robotic controller, and when the robotic controller tells the bin picking studio to do something, bin picking studio obliges. Okay, let's check so the green ones are computed successfully. You can see the trajectory. The red ones mean that some waypoint failed. I can preview grasp invariances. So these are basically all that came through that satisfy the grasping angle, because there is one setting that says that the gripper cannot be under too large angle. So when the gripper would want to grasp the part from the bottom side, that is of course not good, not suitable, not correct. So that is rejected. So if you remember, I defined gripping point for this part at the top and at the bottom, and the gripper can rotate 8 times. There are 8 invariances. So when I preview my grasp invariances, these are all 8 steps of the gripper, rotations of the gripper that were considered, and the other 8 from the bottom side were rejected very fast in the beginning of the path planning, because it does not make sense to even consider them, because the angle is too large. The gripper would need to come from the bottom of the beam, which does not make sense. And I can see that for these invariances, all of them are unreachable, because the robot actually is not that big, or based on our joint limits that are employed, the robot cannot actually reach that far. For this red, you can see that in this grasp invariance, the gripper is in collision with the bin model. For the other, again, another bin model, so there is a collision. This is okay. This was computed successfully. There is no collision. Even the collision with the volumetric model, so the volume of the bin is low. It is 1.73%, and I have left it on the default 5%, which should probably be tweaked, because I can see that even 1.8% should be okay. But what went wrong? So something else went wrong. I'm going to go to waypoint tab and see that the start waypoint has been computed successfully. The approach has been computed successfully. We already saw the grasp that was here, the grasp invariances successfully. So something must have been wrong in the approach. Okay. And I can see that there is a collision between the scan and the picked object. So the picked object, when it is attached to the gripper, it is actually colliding with the scan, because the scan is converted to volumetric model also. So here are some small boxes, and this is too close. This is too close. A collision might happen. So the scan is colliding with the picked object in this waypoint. In this case, we could employ 2 strategies. We could either make the D approach higher, or we could do the D approach away from the walls of the beam, just as we were playing with before the lunch, before the break. So you can see that by tweaking the grasping method a bit, you can make even this part pickable. Okay. There is another question. Is it possible to work with one bin until it's empty and start picking in the other one? Same parts in the 2 bins. Good question. Of course, it is possible. But you should do this also with 2 vision systems. So you should have 2 bins. For each bin, there will be different vision system, and each vision system, they would be basically the same. The only difference would be that each vision system would have different bounding box, because the one scanner sees both bins, and you only want to see the one vision system. You only want to see the one bin for which it is intended. And when this vision system, when you request trajectory and you no longer are getting successful trajectories, you are getting the empty scene or no part found or path planning failed error, then you switch the vision systems and you start picking from the other bin. So yes, this is possible. Okay, let's check the settings very quickly. The default values are optimized, so there's usually there is usually no reason to change many settings, especially regarding collision checking. There is option to pick only unoccluded objects. So when the localization tells me that, for example, this object is under this object, so this green one is under this blue one, this green one will be occluded, and it won't be chosen for picking. So I can set this setting on, and the object won't be even considered. These are the colors of the parts I was talking about. Let's actually go through the colors. So the color codes when the part is being calculated is as follows. And the first thing, the first time the part is localized, it is yellow. If it is part from the previous run, so from the bin picking memory, because the bin picking has memory, each vision system actually has memory. That means that each vision system remembers from the past run, from the last run, which objects have been localized and whether the trajectory is calculated for them already and whether it can be reused. If the path planning, if the part is from memory, but the path plan is not valid because it was not computed or there is new collision detected, then the part is pink. And if all waypoints and some trajectories from the previous run are already computed, then the part will be dark blue. If all waypoints are computed, it is light blue. If trajectory has been successfully computed, it is black. And when it is finally ready to pick, it is green. These colors are mostly not visible because the stuff is happening all at once very quickly, so you cannot even see it. You will mostly see just the yellow, orange, and then the green and blue parts. And then, of course, when the trajectory is requested, the object becomes from green, it turns from green to this blue color. And when an error happens, when an error occurs, there are other colors. So we already saw the bright red, which means that one of the configured waypoints has no valid inverse kinematics solution, so it cannot be computed. The system cannot find the set of joint values for the robot that would be suitable in that waypoint. So there is either the waypoint, the position is unreachable, or there is a collision, or something else has happened, and you can always find the reason in the inspector, in the debugging tool. Then there is the occlusion. So if you turn on the setting, the parts that are occluded will be that light green color. If the grasping angle is too high, that means when there are parts that are oriented in such a way that the gripping point is not defined for them in this orientation, then the parts will be brown. For example, for the second object, for the cylinder one that we defined in the solution, if it was oriented with the hole at the top, then we don't have gripping point for this configuration, and the part won't be picked. And Of course, there is the gold or the yellow color, which means that the gripper in the grasp waypoint is exceeding the gripper collision, the allowed volume of the gripper in collision. Okay, and here are the settings. So the collision with the picked object can be turned off. It is turned on by default, and I was already mentioning that it's starting to be considered in the de-approach waypoint. So in the de-approach waypoint, the part is attached to the gripper, and from then on, the part is considered, and collision checking is taking it into consideration. You can also turn off, but by default, it is turned on, the collision checking with the localized objects. So the point cloud is a collision object, but even the localized parts are collision objects, but that can be turned off. So the point cloud is a collision object, and I already said that it is converted into volumetric model. So it in a representation where each point is converted, not each point, but there is a cube, a small cube in each point in space where there are points of the point cloud. So similarly to the gripper volumetric model, the point cloud also is represented by these small cubes, and you can define the resolution of the cubes. With smaller grippers, smaller parts, you need to go a little bit lower. So, for example, I can go to 3 millimeters. Then there is filtration of the volumetric model. So if there are some unfiltered segments in the point cloud that the Foxy control and the scanner settings were not able to filter out, then we can filter them. If there is less than 20 cubes in the volumetric model, they are making one segment. Then there are settings regarding the inverse kinematic solver. Basically nothing that needs to be changed here. Then the path planning, you can have several path planning modes. You can have full path planning, so all trajectories are planned. You can only plan linear trajectories, so only trajectories that are marked as linear. In the default grasping method, those are only the trajectories between the approach and the approach. So from the approach to the grasp waypoint, and from the grasp waypoint to the de-approach waypoint. There are two path planners to choose from. The default one is advanced because it is advanced. It has more options. The standard cannot be customized. In the advanced path planner, you can provide the number of waypoints to be in each trajectory, and some other settings that I do not recommend changing because the defaults are optimized. Then there is this option to prefer linear trajectory, which means that the system will always try to calculate linear trajectory even for the joint trajectories, because the linear path is the smallest, fastest way to get from point to point. So the system will firstly try to calculate trajectory that is linear, and after that, only after that, when that fails, because it is very fast, only if it fails, then the system will try to come up with joint trajectory. Then we have the sorting criteria. We have, by default, we are sorting from up to bottom, from top to bottom. So the top parts are picked first. There is a vector that is defined to point downwards. So 0, 0, -1. We are pointing downwards in the warp coordinate system. We can also sort by the not closest point of localized object. So we are now taking into consideration the highest point on a part. We can take into consideration centroid of the localized object, or we can sort based on value of the overlap from localization. or we can sort by the number of collisions with gripper. So the part that has the least amount of collision with the gripper in grasp waypoint will be chosen as first. Here is the mentioned grasping angle. So by default, the gripper cannot have bigger angle between 2 points and the world z-axis, or it is actually this vector 0, 0, 1, which is the same as robot z-axis or the world z-axis when the robot is mounted vertically. So we can increase this value up to 90 degrees, but that is not very, does not make sense to go to such high numbers. In some special cases, yes, but 50. You see, when you try to pick a part from the side, it will most likely fail because there are other parts on the side at the sides of the part. So most likely the collision checking will detect a collision. So 50 is optimal number. Then there are settings regarding the beam picking memory. So part is remembered if it moved or rotated less than 2 millimeters or 1 degree. Pick failed is a feature. When the robotic controller has some kind of sensor, or the gripper itself has a sensor that can detect that the part wasn't picked. For example, it is under some other parts and the gripper cannot actually grasp it because, or it tried to grasp it with the magnet, but the magnet is not strong enough. You can send a request, just like the scan request or the trajectory request. You just send the request to the beam picking studio saying that the part that I tried to pick is not pickable, even though you provided me with a trajectory, and the beam picking studio will no longer try to provide this trajectory for this object until unless there are no other trajectories. So it will be moved to the backside of the QE of all computed parts. And you can set the threshold for the part to be remembered. So I can say that please remember the path plan if the part moves less than 2 millimeters, but remember the part itself that it is the same part if it moved less than 10 millimeters. So the path plan will be recomputed after 2 millimeters, but it will be still the same part until the movement is more than 10 millimeters. Then there is option to define the symmetry axis for the part. For example, I now have symmetric parts, so I could provide axis of symmetry. This is just in case. The localization would, for some reason, report the same part in each cycle as rotated in other rotation. So if the rotation would be changing, which does not happen in normal situations. And then there is the timeout for trajectory requests. So when the robot requests a trajectory, it must be provided in 10 seconds. Otherwise, an error is reported. And this one setting is the wait time after first object localization, which means that after the first part is localized, we are waiting half a second by default. It can be minimized to 0. We are waiting 500 milliseconds, and only then start path planning. Why? Because in half a second, several parts will be localized, and the best one will be chosen for path planning as the first object. So we are not taking the first part that is localized because the localization is random. It can be not the most suitable part, but we wait by default few hundred milliseconds and then choose the best from the localized objects for the path planning. So this is just kind of optimization. It can be lowered if it is not required for your application. These two initialization settings, in most cases, they are left checked. So the memory is cleared when you initialize any for the new request for vision system initialization is received, and also that if you are using fast scan feature, that the full scan will be will be executed after new request for vision system initialization has been received. So a lot of settings, but most of them are not really relevant in most applications. You mostly just change the resolution of point cloud to optimize collision checking and the number of waypoints in a trajectory. Then maybe prefer the linear trajectory, and all, of course, change the sorting algorithm. Memory usually is enough, the 2 millimeters and 1 degree threshold, but can be for bigger parts, it makes sense to increase these values. Okay, let's actually deploy the solution, but this time let's try with the real robot. So finally, let's deploy our beam picking application. So one more time, let's run deployment, and in the production mode this time, let's check the presentation one more time. So this is the creeper collision sensitivity, where you can see that the model is in collision with the localized object and the point cloud that is in the object. You can see that the gripper collision in the bottom right corner is exceeding the default value of 5%. So this is why the object was rejected. This is the occlusion. So when we allow the occluded function feature, only the non-occluded part will be pickable, will be green. The others cannot be picked until the parts that are occluding them are picked. So you can be sure that in this case, the parts will be picked one by one in a row. The priority options. This is some comparison of the path planning modes. So for the default option where all joint and linear trajectories are calculated, you don't get much, you don't get the highest speed, the shortest cycle times, but there is no risk of collisions. And on the other hand, when you turn off the path planning completely, you get very short cycle times with high speed of path planning, because it is actually turned off. Only the basic stuff is being done by the beam picking studio, but collision, there is a risk of collision happening. So you should only do that if there is collision-free environment. So for example, if you are picking from a plate, from a conveyor belt or something like that, not for bins, especially not deep bins. When planning on the linear trajectories, that is something between. So when you are picking from shallow bins, that is possible to do, to only plan the linear trajectories. Okay. Okay, so before we end, let's actually see the picking for real. You can see that in the production mode, I can only request a scan. No other options for me as an operator to do from the beam picking studio. I'm going to select the robotic program. I'm going to start at low speed. And in this, beforehand, in this robotic program, it is very simple. The robot will move to the home position, a scan will be taken by the extrinsic vision system, so by the big scanner. The robot will pick the part for this vision system. Then, with the picked part, it will go to scanning position with the smaller scanner and scan the other bin. And while the scan, after the scan is done, it will go to the placing position with the first part. And in that time, path planning is taking place. So after it comes back above the bins, it has already computed trajectories. So it requests a trajectory for the other part, picks it, goes to placing. When it leaves the bin, the first scanner, the big one, once again requests a scan, takes a scan, and so on. So we will see in a while. So let's run. Okay, so we are in the home position. I'm going to add some speed because this is very slow. Okay, so the robot picked the part for the hand-eye vision system, but actually there is one small issue. I have different vision system IDs in the solution, so I just need to fix this very quickly. Sorry. So bin picking studio training. The extensive vision system is number 1, unique ID number 1 actually, and the hand-eye is 2. So the scans were switched in the robotic program. Okay, so once again, let's run in the production and let's try once again. Okay, so we are in the home position. Hopefully this time it will be all good. The extrinsic vision system took a scan of the whole scene. The cogwheel part is being localized, patterning is already done, okay. And we are picking the part. Now we are going to the scanning position for the smaller scanner for the other vision system. And while the patterning was taking place, the robot placed the first part. Now the part from the vision system is being picked right after we cleared the volume, the space above the bins. The bigger scanner took another scan, and that is basically the whole cycle that is being repeated. So again, going to the scanning position for the second vision system, placing, and again picking. So you can see that we successfully managed to configure a pretty nice beam picking application with two vision systems, with two different vision systems, where each is of another type. So we have extrinsic one and hand-eye one, and it looks good in my opinion. Please feel free to ask any questions before we end regarding anything in this training. If something wasn't very clear, we can go back to it. I paused the program just to check the other vision system because we didn't inspect it in the simulation mode. But it looks pretty good. Only from the parts that were localized, only the ones that are basically near the walls of the bin, only those failed to be computed because there is the problem with that they are too near the walls. So different grasping strategy would solve this issue. So we can very simply change the grasping method to actually go away from the bin walls or prolong the D approach, because with this one we are colliding with the walls of the bin. And there is a question: could we either get the presentation and the recording of the session? I think this yes, we are recording this training session. I'm not sure whether it will be published, but I think so. You can definitely get the presentation. Actually, the presentation is included in the Beam Picking Studio documentation. So if I go to documentation, and at the top there is the introduction section, and the first thing is training material. So this is the same presentation. So you can find all the stuff that we talked about today in this presentation. And I think that the Beam Picking Studio training will be also published on our channels. One more thing that I noticed, that I did not, I actually turned off during the break, I turned off the bounding box for the hand-eye vision system, because I remember that I did not configure it, sorry, in the correct position because the bounding box is tied to the position of the scanner. So for my hand-eye vision system, if I'm scanning from this one single position, I can use it, the bounding box, but it should be configured when the scanner is in that position. So you can see that I have also parts from the other being localized, which is not correct, but I can run the program. And actually, right now the part is being picked. So what I will do is that I'm going to pause the scanner in the correct position. And this is the position. And in this position, I should configure the bounding box. So for this, I should actually start locate, enable bounding box. And just very quickly put it here. So we do not have parts localized in the other bin. The parts, some features of them are very similar, so it can happen that the part, even though they are different, that this part is localized in the other bin. Okay, save configuration, and let's deploy the solution once again. And let's let it run for a few times, for a few cycles. I will take the camera closer to the robot so we can see. Okay, we have one more question. Is it possible to pick two different parts from the same bin? For example, first one type and then the other type. Theoretically, it is possible, but for that you of course need two vision systems. And one more thing that needs to be confirmed is that the localization can be configured in such a way that only one type of part will be localized when two types of parts are on the same scan. Because in this case, if we are saying that the parts are mixed together, so they are not in the same bin, but on the other sides of the bin, then we cannot use bounding box or something like that. And we need to make sure that the part is that only the one part is being localized, the one type of part. So in theory, it can be achieved, but I would always recommend picking one type of part from one single bin. Okay, if there are no other questions, I thank you very much for your attention. I hope you enjoyed this training session. It was my pleasure to spend this time with you, and I will leave the rest for the František who joined us again.
Thank you very much, everybody, for attending the bin picking studio training. Patrick, thank you very much for very nice training. And I would like to just say a few words at the end. If you have any inquiry for the bin picking studio, please contact sales@photoneo.com. And if you have any further technical questions, please contact support@photoneo.com. Just one small notice, after attending this training, you have a unique opportunity to buy bin picking studio demo for a special price. The price depending on the scanner, which is included in the bin picking studio package. So don't hesitate to contact our sales, and we are going to send you the inquiry and offer as soon as possible. Thank you very much.
Okay, with that said, let's wrap this training up. So once again, thank you, and have a nice rest of the day. Goodbye.